Okay, so it's 21st of June 2022. Let me see, there are some messages here at the bottom, and let's see here. Okay, thank you, good morning. And here you go. Let's go back to the simulations, right? That I was showing to you before. Sound. So here you go. You can see my screen, right? Okay. So we are talking about sound waves. Let's go back here to my notes. This chapter 17 is about sound waves. Okay. Here you go. The waves we saw so far are what we call transversal waves. Okay. In the case of the transversal wave, okay, the disturbance propagate, the disturbance of the medium, by the way, let's put this way, disturbance of the medium is along a direction. Let me see here. No, it's not a disturbance. Let's put it in a different way. You know, waves we saw so far are what we call transversal waves. Transverse waves. In the case of transversal wave, let's put transversal waves. The particles in the medium move perpendicular to the wave. Okay, the wave itself is the disturbance, okay? To the wave or the disturbance in the medium. Okay? That's how you should look at it. In the case of longitudinal waves, okay, the particles move. Let's see, not the particle moves, the particles in the medium oscillate is better, perpendicular. And here too, the particles oscillate along the direction of propagation of the wave. That's the difference between longitudinal and transversal waves. Okay. So sound is a longitudinal wave. Sound is a longitudinal wave. Whatever we hear is a longitudinal wave. Whatever reach our ear, right, is a longitudinal wave. Okay. It can be modeled, you know. Sound can be modeled here. Sound can be modeled. Several air particles oscillating along the direction of propagation of the sound. And here you go, and you saw a model of a sound wave before. Here you go, right in here. So that's a very simple model. I'm assuming that you have the sound wave that's just like a laser, right? Everybody has seen a laser before, right? Well collimated wave that is restricted only to this column here. Sound is not exactly like that, but you know, but we can picture that like that. Actually, you can get a sound wave like that. Yes, if you have like a tube and constrain the sound within a tube. Within a tube, yeah, it's gonna look just like that. Okay. And there are regions of compression. Okay, there are regions of compression and rarefaction right in here. Okay. Air particles are compressed at a given point, and another region they are, you know, they're further away from each other. This region here is a region of higher pressure. The closer the particles are, the higher the pressure you have. And here is a region of lower pressure. The difference in pressure is very low, okay? So we have this position here of the particle. Okay, here you go. The position of the particle is modeled in this way. Let me write that down here in the notes. Here you go. Sounds a longitudinal wave and can be modeled, right, at several, and it can be modeled as several air particles oscillate along the direction of propagation of the sound. Okay. The displacement of the particles from the position of equilibrium, okay? It's not the position, but the position of the particle itself, but just the displacement of the particle from the position of equilibrium is given by, I can write that down here. Here you go. You start like that, and then we move on, and then we're gonna, what's going on? Here you go, S, okay? I'm not putting X because I don't want to mix that up. I don't want to mix up the oscillating position of the part, or the oscillation of the particle is the position, right? So it's S max. Oh, Here you go. He has this funny way of, here you go, cosine. Okay. At this point in time, you know, you could. So now you decide what's better, right? What you think is better. You either write that down as X minus VT, right? Or the book. Many books out there, they write down in terms of the omega, right? Kx omega t. I prefer the first way, right? You put omega here. So you decide which one is better for you, either this relation here or this relation. I prefer this one because it gives you an intuitive way of remembering the equation, because this thing is just like the kinematic equation that you have learned, right? And then since the argument of the cosine must be dimensionless, this factor here, which is in meters, must be multiplied by another parameter that has a unit of the inverse of the meter. K is 2 pi over lambda, right? So that's what we have. Okay. The particle is not moving along with the wave. No, it's not. It's not what happened. The particle oscillates in a given position around the position of equilibrium. Okay, so here you go. The particles, in this case, the air particles, do not move with the wave. Instead, it oscillates. The particles, they oscillate, right? Instead, they oscillate about its position of equilibrium. They oscillate about its position of equilibrium, just like you saw before. So going back to this simulation, here you go. A bunch of particles here, okay, and I'm gonna put a t equal to 0, a time t equal to 0. You know, look at what I choose for the amplitude. The amplitude is that S max that you saw. I choose an amplitude of 0.4. Okay, this is too much of an exaggeration, okay? In a sound wave, it's not that much. It's very little, okay? It's in the micron size. But in order for you to see the phenomenon of the wave, I'm putting this large amplitude here. Okay, and as I go along, here go t equal to the period is 0.4. I put a lambda of 2 meters. Yeah, let's put 2 meters. Let's say, yeah, that's 2 meters. The amplitude is 0.4. And like I said, this amplitude here is an exaggeration. It's not that high of an amplitude. The amplitude is much less than that. Let me cut down in this. Let's see, this one is gonna be minus half until half. Okay. Let's see if it looks. No, it doesn't look good, right? Let's keep it the other way. Let's keep the other way. Good. Yeah, let's keep this way. So what you see here is exactly that equation that you saw. Okay, here is the amplitude, right? 0.4. The blue symbol coincides with the blue surrounding here of the cell. Cosine 2 pi over lambda f. F is lambda, okay? B2, what's B2? B2 is the x position, and G2 is the velocity. I'm putting a velocity of 4 meters per second. No sounds go faster than that, right? You know that. But here is T, okay? T is H. What's B2? What's B2? B2 is the position, right? This particle here is oscillating about a position of 0. Okay, the position of equilibrium of 0. X, don't forget, X is the position of equilibrium. It's the position of equilibrium of the particle. This very first row of particles here right now has an amplitude of 0.4. Okay, it's displaced let's say 0.4 meters from the position of equilibrium. Okay, that's what it's doing. Oscillate. And if you go ahead, he goes 0.1, right? You can see it's closer to the position of equilibrium, right? Let's see, let's go 0.02 instead. I think it's better. 0.02, here you go. 0.04, going closer and closer. 0.06, 0.08. You can see the particles 0.1 getting closer and closer to the position of equilibrium. I know that the position of equilibrium is 0.125. Here you go, at time t 0.125. See the particles here at the position of equilibrium. And I know that for this specific, and then let's say 0.13. Let's see what the Yeah, 0.13. What happened here? The particle disappeared, right? The particle disappeared because because it's at a negative position in the axis. So it would be better if I go a little bit further right in here. So you can see I'm gonna put 0.1. No, not 0.1, 1.0. Okay, now I can see, right? And let me also put this axis somewhere else. You go, must be here, axis position, axis option, minor, low axis, axis value. Where is the axis position? Right. Yeah, I don't like those numbers here. Yeah. Let's see. Well, I'm gonna leave this way. Otherwise we're gonna spend too much time. Okay, so let's see. Let's go to 0.14 now. Okay, so we see the particles here moving into the negative region, right? 0.16. Okay. 0.18. 0.2. Okay. Instant of time 0.2. Look at the S position here, minus 0.32. You should go all the way down to 0.4, minus 0.4. 0.22, here you go, it's getting closer, 0.37 right now, right? Let's see if we can go 0.24, maybe I'm gonna overshoot. No, I didn't overshoot, that's good. It's almost minus 0.4, right? So now this particle here, this row of particles should start going to the right. No, it didn't yet. Okay, it's momentarily at rest at this instant of time. Let's see, minus 0.28. Okay, now it's going back, right? Now it's going back. Okay, so this row of particles here is oscillating around the X position equal to 0. Okay, this row of particles oscillating with an amplitude of 0.4. Okay, so go ahead, understand here what you have. It's compression. In between the compressions, you have a rarefaction. Okay, compression, rarefaction, and somewhere between the compression and the rarefaction, midway of the compression and rarefaction, you have the particles at their position of equilibrium. Each of those rows of particles have their own position of equilibrium. Each of those rows of particles have their own position of equilibrium. Okay? That was something that took me some time to understand when I was doing this simulation here. Each row of particles has their own position of equilibrium. Let's take a look at the value here. See that? That's the position of equilibrium. Okay? And then in the next one, here you go. That's the other position of equilibrium. There's a difference here, right? Those values do not change. And then we have another position of equilibrium here and so on. Okay? They are oscillating about the position of equilibrium. So what we have again, compression, rarefactions, compression. And between the rarefaction and compression, we have the particles that are exactly at the position of equilibrium. Exactly at the position of equilibrium. Somewhere, let me see. Somewhere it's this one here should be 1.6, right? We're talking about a wavelength of 2. So around the 2.6, we're going to have a rarefaction. 2.6 around here, you know, maybe in this region here. And around 3.1, you go, must be around here. Yeah, 3.1 between those two particles, right? Those particles are exactly at their position of equilibrium. Somewhere between those two particles, they are at the position of equilibrium. 3.1, let's take a look. Okay, 3.1. Around here, the particle should be, let me see, at the position of equilibrium. Oh, actually, it's a little bit further down. Okay, right in here in this region is 3.6 actually. See that? The delta X is close to 0. Delta S is close to 0. Okay. Notice that S is 3.6, X is 3.6 as well, right? So when you are between those 2 points, 3.6, let's see. Yeah, 3.6. Okay, so here you go. There is, let's document that, right? Here you go, 1.6. Yeah, right in here. Okay, so let's document that here. Notes, okay? Their particles do not move with the wave. Instead, they oscillate about this position of equilibrium. Along the wave, notice that along the wave, we have compression and rarefactions. Okay? We have compression, rarefactions, and rarefaction. Okay. Regions of compression. In the regions of compression, the pressure is higher. Okay, in the regions of rarefaction, the pressure is lower. So the equation for the pressure is given. We can derive that, but I'm not going to derive. Okay, the book derives that for you by the following. Here we go. Let's see here. The equation for the change in pressure is given by the following. Okay, it's going to be like that. Delta P is going to be given by delta P max. And there is an interesting relation between this displacement and the pressure. You know, they have a phase difference of 90 degrees. If here is cosine, here is going to be cosine. Okay, so here you go. P max. What change? Okay. Can you memorize that? Okay. I'm not going to prove that, but the book does the proof there for you. Rarefaction. Here you go. Okay, like that. Okay, so that's what we have. Let's go back to the, I'm going to mark the places where, you know, the displacement is close to 0, right? Here you go. This region. Here you go. This region. Let's go. You got another region here between those, the displacement of the particle close to 0. All right, here you go. Note, see that there is a distance of 1 meter, 0.61, right? Approximately 1 meter, approximately 1 meter. Let's take a look at those positions where the particles are very close to the position of equilibrium. Okay. Here you go. Let's take a look at those positions, right? Very close to the position of equilibrium. Here you go. Around 0.61. 0.72, right? 0.61, 0.72. Let's see, this one, no, this 0.38, 0.61 right in here, and 0.72 is right, oh, not 0.72. Interesting. 0.61. Ah, interesting. He didn't plot everything, huh? Okay, it's not 0.70, it's 0.8. Okay, it's 0.84. I gotta look at 0.84. Okay, he goes. I was looking the wrong place. 0.61 and 0.84. We have to look at this guy here, right? That's why we have to look at this column here. It's not 0.72. Okay, so anywhere between here and here, we have this region of rarefaction, right? And the region of rarefaction, by the way, coincides with the point where the particle is in equilibrium. Okay, make sense? Okay, ideally we should have been seeing here delta S of 0, right? But it didn't get exactly delta S 0. It's a matter of tweaking a little bit more the program, so you can, but it's close enough to 0. This point here is close enough to 0. So let's write that down here. Here you go. Regions of rarefaction or low pressure, right? You go. Comparing these two equations and looking at the simulation, we now see the following. 1, regions of rarefaction or low pressure correspond to a point where the particle, the air particle, right? Let's put here the air particle is at the position of equilibrium. Okay, position of equilibrium means delta S equal to 0. Okay, delta S, let's delta S equal to 0. Let me use this one here. Or delta S equal to 0. Okay. What else? You know, those are the type of things that books don't teach you. Okay, you find that out only after you go through the trouble that I went to do this simulation and all that stuff. But it helps understand. Now, what about the next position of equilibrium? Here you go. Is like around 1.6, 1.63, 1.61. Let's take a look at 1.63, 1.61. Okay, yeah, around here. See that? That's a position of, that's a region of high pressure. Okay, high pressure. So not only, so just like the regions of rarefaction, regions of compression or high pressure also correspond to a point where they are particular at the position of equilibrium, or delta S is equal to 0. Okay, at their corresponding position of equilibrium. Okay, why is that? That's because we have this 90-degree difference between pressure and displacement of the particle from the position of equilibrium. That's why. Okay. What else? What else can we learn from that? Here you go. Rarefaction, you know, rarefaction and compression, right? Compression. So anywhere between those 2 points, okay, anywhere between, here you go, those 2 regions here. So let me see, from 6 to 16. we should be around 11, right? Here you go, right in here. We have maximum displacement 0.399, okay, which is the amplitude, maximum displacement of the particle from the position of equilibrium, which correspond, by the way, to a pressure that's to a change in pressure that's equal to 0. Okay. So here you go. I'm gonna put it as a red color. Let me see if I put another red color. Here you go. Here's another red color, right? Close to 0.4. Here you go. Another one. Red color. Here you go. Another red color. Do you see what's happening? Position of maximum amplitude. No, that's not this one. It's this one here. 3.39, very close to 0.4 maximum amplitude. At the position of maximum amplitude, you're going to have what? That's kind of a little bit not obvious, right? When the particle is a maximum amplitude, the change in pressure is 0. Okay, the change in pressure delta P is 0. Here you go, another position here of maximum amplitude, but in the, here you go, and so on, right? I'm gonna put that. At those positions listed here in 0 is a node. Is a node in the pressure. Is a node in the pressure, not a node in the position, right? In the displacement, not a node in the displacement. Okay. Now, let's go back here. 3, right? 3. Regions where the displacement is the displacement. Let's see. Yeah, the displacement from equilibrium is maximum. Okay. In our simulation, this corresponds to delta S equal to plus and minus 4 meters. Delta S equal to plus and minus 4 meters. 4 meters, no, 0.4 meters. 0.4 meters. Okay. Corresponds to a change in pressure, delta P, correspond to no change in pressure, or delta P equal to 0, or delta P equal to 0. Okay. Regions of rarefaction or low pressure correspond to a point where air particles. Regions of rarefaction or low pressure. Okay, I'm gonna put like that. Delta P, low pressure. Delta P equal to minus delta P max. Okay. Correspond regions of compression or high pressure, delta P equal to plus delta P max, right? Also correspond to a point where the air particles, right, are at the position of equilibrium. Air particles, the plural, are at the position of equilibrium. Okay. So what is a valley or a peak in pressure? Is a node in the displacement. Okay. Whatever is a valley in the pressure corresponds to a node in the displacement. Whatever it's a crest in the pressure also corresponds to a node in the displacement. Okay. Regions where the displacement from the equilibrium is maximum, right? I have to write that down here. Maximum in our simulation, this corresponds delta S plus or minus 4 meters correspond to a change in pressure, delta P equal to 0. Right? So we can, if you're going to where the displacement from the equilibrium is maximum positive, right? This corresponds similarly, okay? Regions where the displacement for equilibrium is maximum negative. Let's see, is minimum negative. Let's put this way, minimum negative, right? It's better. Minimum negative. In our simulation, this corresponds to delta F. Correspond to a change, to no change in pressure, or delta P equal to 0. Let's see if I can get, let's see here. Someone has a message here, Professor. I need about 10 minutes to use this restroom. Okay, we have to take attendance. Oh yeah, we'll take attendance very soon. Hang in there. 8:26, right? Let us wait for the break, right? When you get to the break, I'll take attendance. Remind me of taking the attendance. And we have this graph. Let me see if I have here in my notes. Now let's go to Wiley Plus, right? Wiley Plus has a graph there of the pressure and the displacement. Enter password. What's my password? Now the book is here. Chapter, let's see, course resources. Launch, textbook. Yeah, the lab report is due before 12 noon, okay? The report for the lab is due before 12 noon today. Wave 717, here you go. Let me see if I can find the graph here for you. Here you go, it's the same illustration that I came up, right? It's fancier, of course, right? Than the one I have. Let's see if I get it. Yeah, here you go. That's the graph I want. See the pressure and the displacement from equilibrium. They are offset by 90 degrees. Where is a peak in the displacement? It is a node in the pressure. Where is a node in the displacement is either a peak or a valley in the pressure. Okay, so there is this. Similarly, a valley in the displacement corresponds to a node in the pressure. Let me just copy that here. This is exactly what we get there in my simulation. Snipping. Okay, and paint. Let's get that into paint. Okay, here you go. Oops. Let's see. Right in here. Node. Yeah, this graph is not a little bit off, right? It's a little bit off. I noticed that. It looks like they didn't plot it properly. Okay. See that it doesn't correspond exactly to the peak, right? Doesn't correspond. So I suspect it. Yeah, it's a little bit off, but you know, looks like they made a mistake here in this graph. But this one seems to be fine, right? This point seems to be fine. And so on. Okay. Yeah, just a little bit off for some reason. So yeah, this one is is very off. Yeah, there's a little bit. Yeah, that doesn't look like they plotted properly because there's a small difference. Okay. I was suspecting that. Yeah, this one seems to be fine. This one seems to be fine. The valley corresponds to the node, right? Oops, what happened? And so on. Okay. That. Okay, we hammered enough on that, right? You get the idea? Someone's trying to come in on board. There is a relationship between the maximum pressure and the maximum displacement. I'm not, like I said, I'm not going to derive it. It's possible to derive it. The book does that for you. There is a relationship between the amplitudes of the above equation, the amplitudes of the above equations. Okay, so delta P max is equal to what? Is equal to the velocity, is equal to the times the density of the material. In this case, in our example, that's the air times omega times the maximum amplitude of the oscillation. That's the relationship between delta P max and S. You know, in real life, we have an example in the book, okay? In real life, the, you know, see book example. Delta P max, when we are talking about the regular pressure, okay, we're talking about the air pressure. We are talking about 1 atmosphere. 1 atmosphere is approximately 10 to the fifth Pascal. But this delta P max here is very small, okay? In real life, delta P max is very small compared to the actual air pressure. Okay, air pressure, which would be the position of equilibrium, air pressure is 1 atmosphere, which is approximately regular air pressure, right? Regular air pressure is at 1 atmosphere, which is approximately 10 to the 5th Pascal. It's very good if you have an idea of the values. Okay. According to your book, okay, regular air pressure is 1 atmosphere. Okay. comma, whereas delta P max is usually on the order of 28 pascals only. Okay. Notice that the thing is less than 1% of the regular atmosphere. So all those compressions, let's go back to my simulation, right? My simulation, here you go. My node is somewhere around here, right? Here you go. My node is somewhere 11. Let's see. 1.53. 1.53 is 1.53. Yeah, around here. Around here. High pressure is right here in the middle, right? 1.53 corresponds to a node in my pressure, the node in my pressure, okay? Node in my pressure. So in this region that you see here, you have 1 atmosphere, 10 to the 5th Pascal, in this region right here, okay? Maximum displacement of the molecules correspond to a node in the pressure. So that should be 1 Pascal, 1 atmosphere, 10 to the 5th, 100,000 Pascal. Whereas in this region here you go, 1.63, even better. This one is closer, right? 1.63 around here, somewhere around here. Yeah, 1.6 should be, you know, higher pressure. 1 Pascal plus 1 atmosphere, right? 100,000 Pascal plus 28 Pascals. In the region of, in the region of rarefaction should be 100,000 Pascal minus 28 Pascal. Okay, so that's how it is. Let's see. So here you go, 28 Pascal. So we can state the following. We can state the following. At the regions of compression, the pressure is 100,000 Pascal plus 28 Pascal. It's a very, it's a small disturbance, okay? It's a small disturbance. Compare 28 to 100,000. 28 to 100,000 is almost nothing. Is less than, you do the math, right? Let's get that. 28 divided by 100,000. That's why we call it a disturbance. That's the real life. $100,000, 1, 2, 3 times 100. Wow, it's 0.028%. In other words, the disturbance that a sound wave provokes in the medium. And by the way, that's for a very loud sound, okay? That's for in the limit of hearing, in the limit that we can stand, the hearing can stand. In the medium, sound wave provokes the disturbance that provokes in the air, in the air medium is 0.028% of the actual air pressure. Okay, it's the same thing. Similarly, at the regions of rarefaction, the pressure is 100,000 Pascal minus 28 Pascal. Okay. And that's a sample in your book, an example in your book. What displacement that is that this corresponds? The book also does that here. How do we know that? We know that by making measurement. Okay, there is a no other way. But the displacement we can calculate from that relationship that you saw in there. If you look at your book, the maximum displacement for the displacement, the amplitude is on the order of microns, according to the book example. This is 11 microns. 11 microns. Okay. So when I say that I exaggerated here in my model, I'm not kidding. Okay. I'm not kidding. I'm using an amplitude of 0.4, but I'm using an amplitude of 0.4 so we can see those regions of rarefaction and compression more easily. Okay. If I were to do it in terms of microns, it would be difficult to see it. Okay. So that's what we have for this part. That section, what we did here is sections. Okay. So far, sections 17-1, 17-2, 17-3, 17-4. 17-4. That's what this is all about. This, what I have covered so far. Those 4 sections in the book. Now we can start talking about interference. 17-5. What time is that? 8:56, right? We're getting to our, yeah, let's take a break. But before we take a break, let me take attendance. Almost 1 hour that we have been doing that. Let's see, P39. Attendance roster. Lecture. Today is 78. Today is the 21st, right? Yeah, today is the 21st. Let me go further than that. Here we go. Wasn't nice to have a holiday yesterday. I miss holidays. Here we go. Toby, are you there, Toby? Toby just joined us, right? Yeah, okay. I hardly heard you, Toby.
What?
I hardly heard you, but you are there, right?
Yeah.
Okay, good. Harun, are you there, Harun? Harun, let's see here. I think Harun had joined us. Yeah, he's here, but he's not answering. Must be away from his computer. I'm gonna put a star here. Musa, are you there? I see Musa as well, but I don't hear you, Musa. I'm gonna put it a star here. Zachary, are you there, Zachary?
Yes, I'm here.
Okay, good. Thank you. Elena? Good. Thank you, Elena. Crystal? Luis Crystal? I can't hear you, Crystal. Did you say anything? Okay, I don't see Crystal in the list here. Okay, so I'm gonna put a 0. Brian Spino. I don't see Brian. Robert Faust. Okay. No, Robert, not you, Pedro. Here you go, Robert. Thank you, Robert. Pedro is there, right? Lawrence Flores, are you there, Lawrence?
Yeah, I'm here, Prof.
Okay, thank you. Daniel Freire.
Here.
Okay, Amalia Gale.
Here, Professor.
Thank you. Tiffany Wang.
Here.
Okay, Olivia Kroger. Olivia, I see Olivia. Let's see. No, Olivia is not around today. Yeah, someone is Dave, right, Dave? Someone is messing up with my screen here. Can you please erase it? Daniel Young. Thank you. Daniel. No, I don't see. Oh yeah, Daniel Liang. I see it here, but he must be away from his computer. I'm gonna put a star here. Sarina. Are you there, Sarina? Sarina is listed too, but I don't hear from her. Here you go, star. Anthony Lopez. Good, thank you, Anthony. Chuk Lu. Are you there? Okay, thank you. David Maes, right? Dave. Okay, I want to hear from you, Dave. Okay, good, thank you. Either type there in the chat box or just speak through your mic. Ryan's there, right? Good. Alexis Nigret. I see Alexis.
Here.
Okay, thank you. Daniel Nwagbu.
Here.
Thank you. Dave Nwagbu.
Here.
Okay, Claire Ottinger.
Here.
Thank you. Jennifer Ramirez. Good. Noah Raymond.
Here.
Next is George Risk. Okay, thank you, George. Safi.
Here.
Next is Natalie Santiago. I didn't see, is Natalie there? I didn't hear.
Here.
Yeah, okay, now I heard. Okay, thank you. Nathan Silva. Next is Darnice Simon. Good, thank you. Kenny Villagomez.
I'm here, Professor.
Okay, Nolan Williams. Thank
Here.
you. Nolan's there, right? Okay. Meng Shu. Meng Shu, okay. Let's see, anybody else? Olivia Song. Now, what about Ki So? I don't see Ki So in the list. Okay, and now let's sum everything here. Oh, interesting. $28. And what about the students who I didn't hear? Daniel Liang, are you there? Sarina Lobana. Okay. Okay, good. Thank you. What about Harun and Musa? Are you there? Okay, so let's go for a 9:02 right now. Let's go for our break. It's notes break to 9:03. Let's see, 9:18. Okay, I will see you soon. I'm back here. And so before we move into the next section, let's, let me tell you something about the representations of a sound wave, okay? So, here you go. Before we get into section 17.5, let's talk about the representation of a sound wave. Okay, you have seen this representation that's one of the representations. Okay, that's how you can represent one possible way of representing a sound wave. Let me go back to what I have here. The drawing's gonna, okay, better, good. Think about that. Think about representing a sound wave in the exam. In this way, in exactly this way, drawing every little dot, artifacted and compressed, and so on. It should take a long time, right? Drawing each dot here, even the computer program, it took me some time to draw something like that, to plot something like that. Okay, but that's one possible representation. There is a simpler, but there is also a simpler representation. That's easier, to represent. Okay, let me show you here in my notes. Here you go. That's the more difficult one, more troublesome to draw, because it takes some time to draw something like that. But it's also a more realistic interpretation. It's a more realistic drawing of what happens at the microscopic realm. Okay, but a simpler representation is the next one that you're going to see here. We see these types of representation as well of sound waves. Okay, instead of drawing each dot, that, as you saw, is far less work to represent regions of compression as a solid line. Okay, compression here, compression here, compression here. Distance from here to here is a wavelength. Okay, and the region of rarefactions as a dashed line. Rarefaction here, rarefaction here, rarefaction here. Okay, and the position of equilibrium as a single line. Equilibrium here, right? From this position of equilibrium to this position of equilibrium, you have half of a wavelength. A full wavelength would be from one position, would be from each other position of equilibrium. Okay, each other position of equilibrium would be a wavelength. That's one way. And then there is a third way as well. We can represent also a sound wave in the same way that we represent a transversal wave. Okay, here's the axis S, the displacement from the position of equilibrium. This is not the pressure. And here is the x-axis. Three different ways. We can even introduce a fourth different way. Okay, three different ways of representing a wave, a sound wave. Let us plot this one. Okay, let's write that down here. At least three different ways of representing a sound wave. One. Oh, okay, thank you. I'm not sharing the screen, right? Yeah. Okay, so let's start all over again. Yeah, don't be ashamed of remind me of that. What about now? Can you see it? So let's go back. Let's go back what we are talking about, right? So here you go. Three different ways of representing a wave, a sound wave, right? You either draw each dot represents an air molecule, but it's lots of work to do that. The closer each dot is, The higher the pressure is, the further apart they are, the lower the pressure is. But like I said, representing a sound wave in this way is too much work, takes too long of a time. So people figure out a different way of doing the same representation. Okay? Instead of drawing each dot, you just go ahead, represent the compressions by a solid line that you have here. Another solid line, another solid line. The distance between those two solid lines is the wavelengths. The distance between those two solid lines is the wavelengths, and so on. The rarefactions are represented by the dashed line. The distance again is wavelengths. From here to here is half of a wavelength. And finally, the position of equilibrium we represent by a single dash. A single line. Would have even better represented by a dot, even better if you had represented by a dot. And the distance from one dash or one dot to another one is half of a wavelength. The full wavelength is every other dash. That's a very nice representation. Another way to represent is just by drawing the S, the displacement along the y-axis, and the position, right? X. You get this sine or cosine representation. Let's represent that. Here you go. I'm gonna plot that right in here. Right, so here you go, insert. No, it's not what I want. I want this one here. Something wrong here. Let me see. I know why. Yeah, there's a reason for that. Okay. Let me see if I can do it better. Okay, I shouldn't be using this one. I should be using this one here. Yeah, now I got it right. Okay, that's the displacement. This one is the displacement from the position of equilibrium. That's the position of equilibrium, and that's the displacement from the position of equilibrium. This one here is just the position of the particle. Okay, the position of the particle along the x-axis. That's what it is. Okay, so that's another representation of our wave in terms of the displacement, right? I can label it delta S here. Let's put now let's represent in terms of the pressure. Let's make our representation in terms of pressure. I want to do that. Equal pressure. It's gonna be a sine. This one here. I'll just want to the delta P. I'm not gonna sum that. Okay, instead of cosine is gonna be a sine. Okay, but then the amplitude here is gonna be different, right? The amplitude we're going to copy from the book. Okay, go. Okay, this amplitude here should be the velocity, density, and omega. The velocity, what the velocity is? Okay, the velocity is right in here. Velocity. The density, I have to use the density of the air. Okay, the density of the air is what? What is the density of the air? Minus water is 1, right? 1 gram per cubic centimeter. There is, you have here in your book the density of air. You must have it. fluid, material, air. 1.21 kilograms per cubic meter. 1.21 kilograms per cubic meter. Omega, what's omega? Is 2 pi f. Let's see if we have the, yeah, we do have this omega is 2 pi f. Okay, in this case, it's going to be the t. 2 pi divided by t, and we put what else? And then we have multiplied by the amplitude right in here. Multiply by the amplitude of the wave. What's going on here? Let's see. He didn't like it. Yeah. And okay. Okay, should be a, okay, now we should have it right. Okay. I'm doing that in the fly. Hopefully I'm not making any mistakes here. Okay. Let's see. There's a sign. Yeah, okay. I don't need to go all the way down. I can stop right in here. And now I can plot my delta S, right? I'm gonna plot both my delta S and my P. Let's see how it looks like. Let's see. No, it's not gonna work. Wait a minute. Yeah, there is a way to make it work. Okay, so this one here is the pressure. This one here is the displacement of the particle, and there is a way to get a second graph, a second axis here. Let me see if I remember how to do that. Anybody there? Anybody out there remember how to do that? There's a way to put a second y-axis here, so those two are in the are more easily visible. Let's see how we do that. If you remember, let me know, okay? Let's see, logarithmic scale, tick mark. And then there's a way to put a second y-axis here. How do we do that? Maximum, I can't remember it right now. Labels, let's see here. Primary, secondary, yeah, here you go. Okay, now we got it. Okay. Okay, so here you go. 90 degrees. And then I'm gonna put some lines, change series chart. I wanna put a, let's see how I'm gonna do that line. Maybe here, no. Oh yeah, that's what I want. Okay, so let's do it again. Secondary, okay. So here you go. Series 1, it is the displacement. Here you go, displacement from position of equilibrium. Amplitude is 0.4, right? This red one is the pressure. It's the pressure. There is a shift in 90 degrees right in here. Okay, 0. Displacement corresponds to minimum pressure, and the other 0 displacement correspond to maximum pressure, right? So those are 1, 2, 3, 4. Let's see here. How many ways of representing the sound wave? That's 1, 2, 3, and then in terms of the pressure as well. 4 different ways of representing a sound wave. We would be using more this one here. This one is the one I'm going to be using the most. Okay, let's document that in the notes. One. Okay, representation of the air molecules in terms of dots in the XY plane. The XY plane. Okay. The closer the molecules, the dots are, molecules, dots slash molecules are, comma, the higher the pressure. Right? Second way, lines and dashes. Solid lines, you go, solid lines and dashed lines. Dashed line, let's see, solid line, dashed lines. And let's put dots here. The solid lines, region of high pressure. Dashed lines, region of, and let's see, region of compression. Let's put it this way, compression. Regions of rarefaction. Right? And dots, regions of nodes in the pressure, right? That's one way. Graph of displacement of particle with respect to the position of equilibrium versus the position X, right? Or graph of the pressure versus the position X. So 4 different ways of representing a sound wave. We are going to, from now on, we're going to use this one here. That's easier to draw, far easier to draw, okay? Sometimes we simplify even further. We're going to use, from now on, okay? From now on, we will use representation number 2, which is far easier to draw. And we go even further, by the way. We go even further. We simplify even further the second representation. Let me see if I have here in my, okay, here you go, right in here, right? Here's the representation. But we go even further in simplifying this representation, by the way, okay? And you're going to see that instead of going through the trouble of drawing the regions of rarefaction, okay? And the regions of zero pressure, we simplify that even further. We draw only the regions of compression. Here you go. This is another representation, much simpler. Okay, much simpler representation, even simpler than what you saw before. What you saw before, okay? Let's see here. Compression. That's what I like to say. I usually like to say that physicists and mathematicians are very lazy people. So they try to find out the easiest, the simplest way of representing a complicated phenomenon. And so that's what we're doing here. We're becoming lazier and lazier, all right? Compressions, 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 that's the wavelengths, wavelengths, wavelengths. Okay. So, well, that was the type of representation that you have whenever you have a sound wave inside a tube, okay? But in general, especially, you know, when I'm here right now talking to you, a sound wave can be represented as a point source in the three-dimensional space, okay? Here is the case in which you have what we call a waveguide, a guide, contraption that guides a wave, like a tube, okay? But in general, you do not have a waveguide guiding the wave. In general, you have a source like a speaker, right, in a room that can be considered a point source, emitting sound waves all around it. And in this specific case, the wave is no longer that plane wave that you saw. See, this is a plane wave here, but it becomes what we call a spherical wave propagating from the point in a spherical fashion in every possible direction. And that's how you represent the spherical wave. Each of those lines are the position of the crest, and the crest is propagating as it moves along, as the wave moves along, okay? Point. So imagine, right? I speak it as just a point source, somehow is emitting sounds in every possible direction, right? Not like your regular speaker. Then the distance between the crests, right, is this wavelengths. Can you pick? That's another representation, okay? And we're gonna get back to this representation here. But before we go there, let's talk about, okay, yeah, let's talk about interference of waves, interference of sound waves. Okay. With a far easier, for now on we use the representation number 2 in an even simpler depiction. We will draw only the solid lines or the regions of compression. Okay, what else? So far we have been depicting sound waves. Let's see, how do I say that? So far we have been depicting sound waves inside a tube, right? Inside a tube. So there are some. Okay, so I have it inside a sound tube, inside a tube. Okay, or also referred as a waveguide. It's possible to do that, right? Everybody knows that you can constrain your sound in a tube. The peaking sound wave constrained inside a tube. Let's put it this way: constrained inside a tube, also referred as a waveguide. However, in general, we can have a point source of waves positioned in free space. With no constraint. With no constraint. Okay. In this case, the wave is said to be a spherical wave. Okay. Spherical wave. And the wave, we call it the wave front, right? Moves in a spherical, the wave fronts. Okay. Represented by the regions of higher pressure. Moves in a spherical fashion. Okay. Just like you saw before. Having said that, now we can start talking about interference. Okay, section 17.5, interference of sound waves. So now that we have Harun and Musa here, right? Let me 1 and 1. We have 32. Interference of sound waves. Okay, so going back to my drawing, here you go. Here are representation of how we can have interference between two different sound waves. Suppose that we put a speaker at a given point and another speaker at another point, displaced by this given distance. Okay. So the sound of this speaker, don't forget, what we have here is not a plane wave, but it's a spherical wave, right? I represent as a plane wave for simplification, for simplicity. But in reality, you have a spherical wave. Okay. So we go this one here. So we have this spherical wave propagating along this line, and you have this other spherical wave propagating this other line. Let me put here the right representation. Here you go. That will be the right representation. And if I want to make it even correct, even more correct, right? Here you go. I gotta put this guy here in a direction that's perpendicular to this line. Get rid of this line, this dashed line here. Oh man, here you go. What a trouble. Ay, 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 ay. Try to make things simpler instead of made it more difficult. I'm going to rotate each of those lines. Size and position, let's see. Height, position, angle. Nope. Do one by one, I guess. Angle, 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 angle. Format shape, here you go, here you go. Height, rotation, here you go. The other direction. Here you go, like that. Okay. And now I'm gonna copy those and paste. That would be a better way of representing, easier way. It's not exactly what's supposed to be, but because I was supposed to be drawing a spherical waves there, right? But at least these planar waves are perpendicular to the path of the wave. So here you go. Like that, right? And so on. Similarly, we have here. I have something similar here. I'm going to make my wave I'm going to rotate my wave so the wave front is perpendicular to the path of the wave, right? Is that 90 degrees? No, I don't think so. Let me get that. I'm gonna get the exact 90 degrees here for you folks. Bear with me. Here you go. Here you go. And format shape. Yeah, I think I got it. Huh? 3 degrees only. That's good. Yeah, and now I can get my wavefront perpendicular to the path. Not yet. Oops. No, yeah, it's close enough, right? Good. So now I can draw my wave fronts here. You go. If I want to put them at the same wavelength, I'm gonna put them a little bit closer, right? So yeah. Yeah. This wave here should have the same wavelength as the other one. So think about 2 speakers. 2 speakers. Tuned at the same frequency. Because they are the same frequency, they're going to be at the same wavelength as well. Provided, of course, the medium is the same, right? Like that. Crest, 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 crest. Eventually, those 2 crests are going to reach this point here. So here you have a detector. The detector can be your ear, okay? And what's going to happen? Your ear is going to hear the wave coming from this speaker and also the wave coming from this other speaker. Because we have those two waves. When it reaches your ear, they are going to interfere either destructively or constructively with each other. Can you picture that? Okay. Reaching this point, there will be some interference of both waves. Here you go. Okay, if you put it right in here, it's going to be the same story, right? It's going to be a different type of interference. Rotation. Let's rotate that. Oh, this one. That's the one I want. Size and position. Here you go. Rotation. Here you go. Somewhat perpendicular, right? I can get this guy's solid. Yep. I want to get rid of this dashed one. I can't. Here you go. Now I can. Another one. Another one, right? Don't forget what you see here is supposed to be a section of a sphere, right? And then I can get rid of this one as well. Here we go. Group, let's see. And now I'm going to try to rotate this thing. Can I do that? Shape, yeah, I can. The other direction, here you go. Should have done that before, right? Save time, here you go. My waves propagating from the speaker to this other position here, okay? So here you go. There's a given distance. This distance, of course, is going to be different from this distance to this point, right? But let's say, because this one is the middle point in this specific case, because this is the middle point, this path of the wave is exactly the same as this path of the wave. So when they reach this position, both waves are going to have the same phase. They travel the same distance and they're going to have the same phase. In this specific case, the interference here at point A is going to be a constructive interference because the waves are in phase. Okay, so here you go. Don't forget, right? You have to visualize a sinusoidal wave propagating right in here. In the other case, they may not be in phase. They may or may not be in phase. They may be out phase. Okay, at point B, sound waves travel a different distance. See, this distance here is different from this other distance. Don't forget, both waves have the same wavelengths, same speaker, same frequency. although they do not have the same phase, they still may form, may be subjected to constructive interference if the difference between the path of the two waves is equal to an integer number of wavelengths. Okay. So, however, if the path is equal to half of wavelengths, 3/2 of wavelengths, 5/2 of wavelengths, etc., the interference will be destructive. So let's say I call this length here L1. This one here is L1. Subscript. And I'm even going to get a blue color. Something like that. Yeah. And the older one, L2, and I'll get that a red color. Okay. So L2 minus L1. If L2 minus L1 is equal to 1 wavelength, 2 wavelengths, an integer number of wavelengths, we have constructive interference. If the difference here is equal to 1/2 of a wavelength, then we have destructive interference and everything else in between. So if you have a destructive interference at this point and you put your ear here, you're not going to hear anything. A little bit off, you're going to hear something. Okay. So that's what you have here. Let's document that. Interference of waves. Consider 2 sound sources, 2 speakers, right? 2 speakers. So emitting sound waves at the same frequency and phase. Okay. These 2 speakers are displaced by a distance d, are displaced by a given distance. Let me see if I put the distance here in there. No, I don't have it. Okay, so I can go ahead and say that the distance between those 2 speakers is d. D. Okay. Go this guy. And we can get another, here you go. Here you go, distance d. Hashed. Okay. Okay, these two speakers displayed by distance D. Okay. If okay, if you are located at the same distance L of each speaker, then the two waves, the two sound waves of the speaker will interfere constructively in your ear. Okay. However, if you are located at different distances from each speaker, say L1 and L2, then you may have constructive or destructive interference. This will depend on the wavelengths of the two sources, and the path length difference, L2 minus L1. Okay, or L1 minus L2. Doesn't matter. Okay, which one we're talking about? So the situation is like that. If the following holds, no. Okay, so if you have something like that, I'm putting the magnitude there, right? The bars. If this path length difference is going to be, 0 lambda, okay, 1 lambda, 2 lambda, 2 lambda, in general, n lambda, okay, n equal to 0, 1, an integer number, right? 2, 3, etc. Then we have constructive interference. However, if, on the other hand, if we have something like that, 1 lambda over 2, right? 3 lambda over 2. 5 lambda over 2. 5 lambda over 2. Or let's say 2n plus 1 over 2. Right? Comma. We have the condition of destructive interference. And you have everything else in between, right? If you are positioned here at this point, you know, you're not going to hear any sound. But let's say as you move along this line, you may hear a very loud sound and then a very low sound or no sound at all. Okay, as you move along this line here with your ear, just because of destructive and constructive interference. Okay, that's what we have for constructive and destructive interference. Let's come up with a sample problem. What you have to know, for practical purposes, okay, it's very easy to memorize what are the possible frequencies of sound, okay? It's very easy to memorize that, it's not difficult. You know, which sound frequencies can we hear? Now it's very good if you can memorize those numbers, because you can have a numeric idea of the type of sound that we're talking about. Sound frequencies, it's somewhere between the sound frequencies that you can hear is somewhere between 20 hertz and 20,000 hertz. Anything below 20, anything below 20 hertz is called infrasound, and anything above 20 kilohertz is called ultrasound. Okay, we can go to the internet and confirm that, frequency of sound, right? Frequency of sound waves, you go. 20 hertz to 20,000 hertz, see that? Can you remember that? That's not difficult, right? That's not difficult to memorize it. Another, something that should be easy for you to memorize, the speed of sound in air is 330 meters per second. Okay, so that's it may vary a little bit because of the temperature, okay, but it's around 330 meters per second. We can look that at the internet as well, speed of sound waves in air. Here you go. Miles per hour, right? That should be 330 meters per second. Okay, 761. Let's convert that, just to make sure that what I have is correct. Here you go. 761, right? 1 foot is approximately 30 centimeters, right? Or 0.3 meter. Oh, 228. There's something wrong here. Oh, don't forget that's miles per hour he's talking about, right? Yeah, it's miles per hour. So we still have to convert it. Let's see, 761 miles per hour. Oh, it's miles per hour. Okay. Not feet per second. It's okay. It's 1,100 feet per second. Here you go. Gotta put it here. 1,100 feet per second. Okay, I got it. Right? 330 meters per second. 330 meters per second. Can you memorize that easily too? Right? Let's do a simple problem, right? Here is 300, you know, find the wavelengths range of sound, of a sound wave, of sound waves. Can you do that? Solution. It's going to be very useful to have an idea of what should be the wavelengths of sound. I'll give you like 3 minutes, and then I'll call you, you know, to see what values you got, okay? Okay, solution. Answer. We're going to need that to solve the next problems that are coming. So I'm gonna give you like 3 minutes. What's gonna be the longest possible wavelengths? What's gonna be the shortest possible wavelengths? Now find the longest and shortest wavelengths of sound waves. One minute has passed by already. Let me drink a little bit of my water. 10:15 already. We need to go for our break very soon. Let's go on. Okay. Are you working on that? That's a very simple problem, okay? I'm gonna call you randomly here. I'm not gonna call everybody, but I want you to be ready to give me an answer. Not this one. Attendance, yeah, that's the one I want. Ten 17. One more minute. Are you all working on that? Yep, I thought you got it. Exercise, simple exercise. Go. A sound wave, or a sound wave. Okay, so I think you should have had enough time to calculate that, right? Let's see. Amalia, did you get your value there, Amalia? Amalia Gale.
I'm still working
Oh, sure.
on
Okay.
the.
Can you go back to the question real quick?
Well, here you go. I want you to tell me given that the range of frequencies of the sound, and given the fact that the speed of the sounding air is 330 meters per second, find what's the longest and shortest wavelengths of the sound wave, of a sound wave. Okay.
Is the shortest wavelength is 16.5?
I didn't do the calculation yet, so I do not know. Are you confident about that? Are you confident about your result?
Kind of.
What about the longest?
I think the answer you gave was for the longest.
You gave for the longest, okay.
0.0165 for shortest.
Okay. Okay, so let's do the calculation, right? That's easy, right? That the short, yeah, those numbers, yeah, rings the bell. I was doing this calculation earlier on. We are talking about 1.5 centimeters, 16 millimeters, right? 16 millimeters and a half for the shortest one.
Yeah.
16.5 meters for the longest one. Let's see if it's that. How do you calculate that? You just use the regular equation for the velocity of a wave, right? Here you go. Lambda, the generic equation for the velocity of a wave, lambda f. We want to know the wavelength, so we know the frequency and the velocity, so we can find what is the wavelengths. That's, the shortest wavelengths is the velocity divided by the highest frequency, right? The longer wavelengths by the lower frequency, right? So just put that in your spreadsheet. All right, here you go. That's going to be 330 meters divided by 20,000 hertz. 1, 2, 3. Yeah, that's in meter. And 330 divided by 20, 16.5. So that's the range of wavelengths that we have for different frequencies. Wavelength that we can hear, right? Wavelengths that we can hear. Okay, around 16 millimeters and a half. The shortest one, 16 meters. That should be high frequency, low frequency, right? Now, let's do another example now. Here you go. We're going to do interference, example interference. So wavelengths, range. It's going to be 0.0165 meters, right? No, it should be greater. Less 16.5 meter. Okay. That's the type of wavelength that we can hear. Another exercise. Okay. Let's say two speakers. Two speakers are Okay. Three speakers are 2 meters apart, 2 meters apart. Meters apart, and each of them emit sound waves with the same frequency, right? And wavelengths. Wavelengths of, let's say, 3 meters. Okay, let's see what the 3 meters wavelength sounds like. Okay, let's before we continue this problem, I want you to find what's the frequency for that for 3 meters. Let's see how it sounds like. There is a, you know, frequency should be 330 divided by 3, right? 110 hertz. That would be 110 hertz. Wavelengths 3 meter, 110 hertz. Let's see how it sounds like. You can go here in the internet. They have sound generators here according to the frequency. Okay, and we're going to be using that tone generator. See that? What's the frequency again? I forgot the frequency, folks. Help me out here. 110. Okay, 110. Let's go back to the internet. I'm going to put 110 here, and you're going to hear what it sounds like. I don't hear anything. Why is that? Oh, do you hear anything? I don't. Volume. Hey, what's going on here? Huh. Do you hear anything, folks? I was playing with that yesterday. It was working. Here you go. Why I don't hear anything? 110. Oh gosh, I don't hear either. Why is that? Strange. Sine. Oh gosh, what a shame. That's so embarrassing. Okay, I can hear 400 hertz. For some reason I cannot. Maybe it's why? Oh yeah, I can hear a little bit. It's a hum. Yeah, it's a little hum. Very low. I do not know how to see. If I stop, I have to increase the volume a lot. And that's because, you know, it's because of the frequency. It's because of the frequency. Let me change the wavelengths. Okay. Do you hear now? I can hear you. Barely. I can hear barely. Okay. You know. Let me hear from. Do you hear? Do you hear the sound? I want to stop it. Start again. Okay. It has to do with the frequency. Okay. My mic is not picking up the sound. Okay. But try to play on your side. You know, let me send you the link. Let me send you the link. You know, if you play in your. Yeah, it's so low that my mic is not picking up, right? But what about this one? Do you hear this one? This one you hear, right? This one I can clearly hear. Yeah, this one you can hear. If I go lower in the frequency, okay? Okay, lowering the frequency. 300, 200. Okay, okay, you still here, right? Let's see 150. 110, we already know that you can barely hear it. You still can hear 150, 200, right? I'm gonna play to 150 now. Yeah, can you hear 150? I can hear 150. I do not know if my mic is picking it up, but if you want to generate it, just look at that link. 110. You know, if Yeah, I can barely hear that.
I can't hear that one no more.
Huh?
Well, I can't. I don't think we can hear that one anymore.
Yeah, I can barely hear. Too bad we cannot go higher in the volume. Maybe I can go here in the volume in my computer. What about now? Yeah. What about now? Yeah, it was just a matter of increasing the volume of my computer. Can you hear that now? Yeah, now you can hear. That's 110 hertz. So it's not just a matter of increasing the volume there of the software. It's a matter of increasing the volume here in my computer as well. Okay, that's what 110 hertz sound like. 3 meters, wavelengths of 3 meters. Okay. If you're a musician, right, you should be able to pick up those sounds very easily, right? If you have been trained in music, you should be able to pick up the frequencies of the sound with your own ear. You should be trained to do that, right? Galileo Galilei himself was music and that helped him a lot to perform his experiments back then at his time. Okay, so what we're doing, going back here to what we are doing here you go. 2 speakers 2 meters apart, each of them emit sound waves the same frequency and wavelengths 3 meters. Right? The question, yeah, okay. Now, let me get you go. This distance here, I'm going to call this distance here L. Okay. So here is 2 meters, right? Let's go back here. 2 meters, okay? 2 meters. The wavelength is 3 meters, so it should be a little bit more spaced. Like that, more like that. All right, you go. Group. Group. Like that. You go. I'm gonna call this distance here L. This is the distance L, 30 meters. Okay. Find, and here is the origin of my axis, okay? Here's the origin of my axis. Find the first vertical distance in which you have destructive interference, okay? Given that L is equal to 30 meters, okay? Let's see, the speakers, let's see here. I'm gonna put here, the speakers are 30 meters away from a distant wall, okay? Find the position of the first point in which you cannot hear any sound along the wall, taking the origin as the middle point between the 2 speakers. Okay. Solution, that's 1030 right now. 10:33 right now. So let's take our break and try to, in this meantime, try to solve this problem. Okay, it's 10:34, 10:35 right now. Let's see, break. And we're going to go for a 15-minute break, 35, 40, 45, 50, break till 10:50. In this meantime, start thinking how you're going to solve this problem. Okay, let me illustrate that for you. So here you go. Here is 30 meters. Here is 2 meters. The wavelength is 3 meters. The distance between those two peaks is 3 meters. Okay, 30 meters. And I want you to tell me what's the first point along this axis, the y-axis. Here's the origin. Let me put the origin here. Okay, the first point here in which you don't hear any, that you have destructive interference, that you don't hear anything, any sound whatsoever. Okay, so that's what I want you to do, and I'll see you in 15 minutes from now. Okay, so should be able to do it, right? We gotta look at the, has anybody done that already? Let's see, I'm gonna call you one of you. That helps the interaction, right? So let's see. Blah, blah, blah. Nathan, do you get that, Nathan? Is Nathan there? I see Nathan here. Oh, let's see here. Yeah, did you solve it, Nathan? Did you solve this problem? Okay. So let me call someone else. Alexis, did you solve this problem, Alexis?
I just sat back down. I'm still working on it.
Okay. Anybody has solved this problem? Okay, let me give you another minute or so. Let's just set that up for you, okay? Okay, so here you go. What you have to do, you have to solve that. You have to use this equation right in here. Because it's going to be the very first position in which you cannot hear any sound. There should be n equal to 0, right? This one right in here. You find the difference between L1 and L2. And then you can figure out what's going to be the position along the y direction. Right? So here you go. The speakers are 2 meters apart. Wavelength is 3 meters. So we're going to have a path length difference of 1.5 meters for the first point in which you cannot hear anything. That's just the path length difference. It's not the final result yet. Right? So here you go. This length minus this length here should be 1.5 meters. Okay. this length minus this length. So that's how you set it up. Here you go. That is the position with respect to this midpoint here. Okay, here should be the midpoint. Here is what you see here is 30 meters, right? And you have to find this position Y. Is this distance here is 2 meters, right? So from here to here is 1 meter. You have this right angle triangle for L2 and this other right angle triangle for L1. Is the speakers are 2 meters apart. So here is 1 meter, right? Here you go. Y minus 1 meter. Y plus 1 meter. Can you picture that now? I'm gonna come up with another slide here for you. Oh, wow, here you go. And I'm going to remove the speaker and just draw the right angle triangle there for you. Making things easier for you. And just, here you go. Here's right angle triangle. Huh, strange. Let me try another one. Strange right angle triangle. This one, that's not this one I want the other in the other way. Well, huh. Let's see. Okay, now I got it. Right angle triangle, here you go. That's one. Did I get it right? Yeah, that's for L2. Setting that up for you. I'm not doing yet. I'm still not doing the origin is right here. Let me mark the origin. Okay. Here you go. The distance from here to here is Y. It's the Y distance that we want to measure. And then I'm going to put the right, let's see, I'm gonna fill it with a different color, right? And then I don't want those anymore. I can remove that too. I'm gonna come up with another right angle triangle, but this one's gonna be a different color now. Here you go. Here you go. Another right angle triangle. Transparent. I'm gonna make it transparent. Huh, strange. Okay, that's the one. That's the one I want. I'm gonna take this one out. I don't need that. That's L1. And we have L2. There you go. Here you go, like that. Did I solve the problem for you? Now that should be easy, right? I don't need that anymore. So let's go ahead and let's write down what's L1 and L2 are. L1 first. Square root of what? L1 is square root of y minus 1 meter y minus 1 meter squared plus, that's y minus 1 meter squared plus 30 meters squared. (30 meters square), right? L2 is similar, but with the difference that we have a plus 1 meter here instead. Now we can use this equation here. That's gonna be equal minus equal I'm going to erase that, right? It's going to be a quadratic equation, by the way. We can make an approximation here to get this thing, this result more easily and quickly. Okay. Let me get my software here. I have a software that can help us solve this problem more easily. Live Math Maker. Here you go. If you want to, if you want to solve it exactly, it's going to take quite some, exercise here, quite some time to solve, but you can also do an approximation. Let's solve it exactly first. Okay. So square root y plus 1. Oh, let's put it, I want to put 1 meter here. Equal, and then we have 30 meters square No, it's minus, right? Minus. And then this one becomes minus as well. .5 meters. Expand. Okay. Yeah, we did that. We did the other. Let's see how you can solve exactly. I'm going to push this onto the other side. Okay, and then I'm going to apply. I'm going to square both sides of the equation. Let's see what we get here. Expand, okay. We still have a square root here that's getting in our way. Let's see if we can simplify anything. Okay, the y square cancel the y square here. Okay, that's good. So we're getting there. Like I said, there is a simpler way to use an approximation. You don't have to go through that, but since we are doing the exact solution, let's continue doing the exact solution. I'm going to apply, I'm going to square both sides again. Okay, here you go. Expand. Let's see if we get yeah, we're gonna get a second order, yeah, square. Here you go. Okay, so we're gonna have two solutions. One is gonna be a positive, the other gonna be a negative. Okay, so let me do that again. Here you go. See? Now I'm going to. So when I take the square root here, I'm going to have a positive and a negative. The negative is going to be below the axis, right? But we're interested just with the positive, about the positive one. Here you go. Take the square root. Calculate. Hey, didn't calculate it. I hate this software. Okay. I'm getting 34 meters. That's a long way, huh? That's a long way. So 34 meters shouldn't be here, right? Should be away from this figure. Is that what you are getting to? Are you getting 34 meters? It's okay. It's okay to put L2 minus L1. Jennifer? Yeah. See, let me see here. Okay. It should be L2 minus L1, right? Because L2 is further away than, is longer than L1, right? See that? It's longer. So what's the difference? Here you go. I put L1 minus L2 here, right? But don't forget that I put a modulus here. Magnitude. Okay? Don't forget I put the. See the magnitude here? Modulus. So it's the same thing. So I'm getting 34 meters that I'm getting for that. This is an exact solution. This is an exact solution. Someone is coming on board here. Let's see, Lawrence. Good. So that's what we have for this one. We can move forward. Okay, I'm going to skip sound level. Skip 17-6, okay? And okay, don't forget the exam is tomorrow, right? Are you ready for the exam tomorrow? Let me hear from you. We have the exam scheduled for tomorrow. If we can finish this chapter. I'm thinking that you know what? I'm gonna give you a break. Let's do exam tomorrow. Exam tomorrow is gonna be just the first 2 chapters, okay? Yes, you will need to use Zoom tomorrow. No, it's gonna be at 12 noon. Exam tomorrow at 12 noon. Okay. Exam 12 noon. No, it's gonna be on Canvas. Exam on Canvas. I'm going to. Yes, we're gonna have lecture tomorrow. Yes, lecture tomorrow. Yes, we're gonna have lecture tomorrow before the exam. We have 20 more minutes here. Okay, and let's cover as much as we can today. Let's see, chapters 15, 16, and whatever we cover today for chapter 17, okay? Exam, open note, open book. Open book. Did everybody buy the Wiley Plus? That's right, 12 to 2 p.m. Well, the study guide is, let me, I'll cover. The study guide is everything that we did here in the classroom, okay? So let me see what I can do. Maybe I'll prepare one tomorrow for you, okay? I'll prepare one tomorrow and let me prepare one right now for you. Let me prepare one right now for you. And we go. We started with chapter 15. Okay, chapter 15. Simple harmonic motion, right? Harmonic motion, and what you have to know about simple harmonic motion. I have amplitude, the core concepts of simple harmonic motion, frequency, and what else? There is one more, and wavelengths. Everything else comes from here, right? Then speed of the wave. Right here we have the period of the wave. I prefer to put the period here. Let me see, period. I'll call period the core concept of simple harmonic motion because it's easier to understand, right? The speed is the wavelengths divided by the period. Okay, and what is the solution for simple harmonic motion? Solution is going to be like for SMH, SHM. No friction, right? No damping. No damping. It's going to be like that. X equal to, I'm going to call it X naught, which is the amplitude. Can be the cosine or sine. And what else? we have here? Mhm. Omega t. Omega t, and we usually have some phase angle. That's the most generic solution for the simple harmonic motion. Okay. You know, if initial velocity is 0, you know, phi is going to be equal to 0 as well. Phi equal to 0. Okay. Initial velocity is 0, phi is going to be equal to 0. So next, and also don't forget the equation, right? Let me copy the notes that we had before. Yeah, here you go. That's the and then you have also the simple pendulum, right? Simple pendulum. The equation, the differential equation for the simple pendulum, strictly speaking, is going to be almost the same. It's not going to be the same, but it can be reduced to the same if you make an approximation. That's the actual, actual equation for differential equation for the simple pendulum. And we have a G over L, right? Like that, simple pendulum. Which, by the way, can be approximated to something like that for small angles. Here is an approximation here for small angles. Today we are going to talk about the physical pendulum. Ends up being something like that too, I'm going to put a value here. Physical pendulum. Then we have a damp with damping. Go. Let's get damped motion. And then we have, I'm going to copy everything here to help me to simplify my task. Yeah, I'm going to copy everything. I don't have to keep on going back and forth. Today is the 21st. With pages, this page is 35. 35. Damped motion. So what's going to be the differential equation? The differential equation is going to be something like that. And by the way, if you look very closely, even though the differential equations look different, their solution is the same. Their solution is the same. All the solutions are in terms of exponential. It just happens that for simple harmonic motion, the exponential becomes a cosine and sine, a regular cosine and sine. For damping, the exponential is a mixture of decreasing exponential and cosines and sines, right? Notice that the solution, even for the forced oscillation, this solution is exactly the same. Okay, so here you go. That's the damp motion equation, and we have the following solutions. Here you go. That's the solution for the damp equation. Okay. Now, whether you have a sine or cosine depends on these terms here in the square root. Okay. That's go. If b squared is less than 1, you end up with a square. But this term, exponential decay here, is the same whether one condition applies or the other condition applies. Whether either condition applies. Here you go. First condition, you go, I'm gonna put this way, right? Second condition, possible condition, here you go. Then we have forced oscillations with harmonic damping, with harmonic force and damping. Let's see here. I don't need that, right? It would be better if I put this one on. Yeah. Yeah, it would be better if I here you go. It would be better if I put it right in here. Simple harmonic, let's see here. Yeah, I got it. $11.22. Here you go. With damping. Okay, here you go. It's better this way, right? It's gonna be either this one or this one. Damped motion. Damping. These two here, let's see. I'm gonna put like that. Okay, and this one here is for this condition. Okay, I can erase that, and then we have the forced oscillations. Here is the differential equation, and here is the solution. The solution that we know it works. See that? Solution like that. Everyone has the same solution. All you gotta do is to put a phase term here. It just happens that the phase and the A, they change if they're different. If you have, for instance, forced oscillation, right? So here go the solution for Where is my solution for tangent? Right in here. That's the solution for tangent of phi. And the solution for the amplitude. And you have to know how this guy here behaves. (11:24), running out of time. Forced oscillation. Here we go. Yeah, I already have that here, right? Here we go. Simple harmonic motion. Here we go. Waves. Okay. What about waves? Okay, solution of wave. Well, let's start with the differential equation for wave. Yeah, it's very important that you memorize the differential equation for wave. Here you go. There's just one type of wave. We're going to see a different type of differential equation for the waves as we move along, okay? This differential equation has two solutions. This one is the forward propagating wave. The other one is the backward propagating wave. Okay. An important type of function or an important type of wave is the, oh, I put a positive here, right? It's supposed to be a negative. Here you go. It's supposed to be a negative. Planar wave. Planar waves. Sine or cosines are planar waves. Okay. We don't need that. And so here now, in addition to amplitude, wavelengths, and periods, now the wave is going to have a variable x, a variable t. And we're also going to define a wave number. And we have this speed of the wave, which is not the same as the speed of the points. Okay. Go. We have other types of waves. Go. We can erase that solution. I came up with some examples. We're running out of time, right? 3 more minutes to go. Okay. Transverse wave. I wrote down the speed of the wave already, right? Oh, here you go. Speed of the wave, of any wave. And then for speed of a wave in a string, right? Speed of a wave. Speed of a wave in a stretched string. Stretched string, like that. Okay, that's the speed of the wave in a stretched string. We didn't derive it, but it can be derived for an electromagnetic wave. That's a generic equation. That's a particular equation for the medium. Okay. I came up also with an equation for the power, average power. Average power of a wave depends on the amplitude. We look at interference of waves. Okay, when we have these two type of waves, we can use a nice trigonometric relation. Okay, which let's see here. It's sine of A plus sine of B is equal to 2i sine of A plus B divided by 2 minus times cosine of A minus B divided by 2. Okay, that's what this relationship is all about. So here goes. So two waves co-propagating, right? Let's see how I'm gonna do that. I'm going to erase that. Right. Here you go. I'm gonna do like that. Here you go. Sine of A plus B is twice half of A plus B cosine of half A minus B. Phasors. I covered phasors as well. Standing wave, let's see here, inflection is just interference of two waves, one propagating forward, the other propagating counter in the other direction. Okay, I see we're running out of time here, so let's stop here. Someone else is trying to come on board, so here you go. 11:31, 32. Let's see. We stopped for the exam. We start in section for chapter 17. Chapter 17. We covered what? Covered 17.1, 17-2, 17-3, 17-4, we 17-5. We skipped intensity. We skipped 17.6. Yeah, okay. So that was gonna be for the exam, okay? 17-1 through 17-5. Okay, so you have to worry about those sections. And then on exam 2, we pick up on the rest, 17-6, 7, right? 17-6, we're not gonna cover 17-6, but we're gonna cover 17-7 in the exam 2. Exam 2, you know, exam 2 includes 17-7, 17-8, okay, 17-9, 10, okay, through 17-10. Okay, so let's go for our break. It's 11:35. Let's see. Can you upload video right after class? Yeah, they can do that. Okay, can we use the white plus for the exam as well because the book is there? Yes, that's right. Open notes, open book. What you cannot have is someone next to you telling you what to do. Well, how to answer. You can have open notes, open books, but nobody, no interaction with anybody. How to do the lab report? Yes, I did show, right? I did show how to do the lab report. Yes, yeah, I did show how to do the lab report. Will you be uploading the study guide Google Drive today? Let me do that right now. Yes, go got one already. Study guide. Let's see if I'm missing anybody. It can be usually plus. Can you upload today's video? Right? Which homework assignment does it correspond to? I gotta look into that, Ryan. I gotta look into that. Okay. But you will be able to figure that out on your own when you take a look at the homework assignment. Let's see, let me stop. Let's do that now. Exam 2, exam 1, exam 1, exam, here you go, exam 1, chapters 15, 16, and sections. Here you go. 17 through -1 through 17. Exam 2 includes exam 2 will include the remaining of chapter 17, okay, of chapter 17, 17-7 through 17, skip 17-6. Okay, so let me erase that. Oh, what did I do here? Yeah. Now save it. I'm going to save as a PDF and I'm going to upload it right now. Let me stop the Zoom recording. Thank you for reminding me. Okay, here you go. This physical pendulum, the theory behind the physical pendulum. So we're going to apply net. You either apply net force or net torque, right? If it's a point particle, you use net force. For a rigid body, you use both net torque and net force. So for the physical pendulum, we use net torque here, and the torque is going to be the torque due to the normal and the torque due to weight. Let's take a look at the physical pendulum. The physical pendulum is right in here. Here you go. That's the type of physical pendulum that we use in our experiments. We have a weight being applied here at the center of mass. And then we also have here you go. We also have a normal here somewhere at this place here. You know, we this in the I'm gonna put a, you know, we do not know what's the direction. I'm going to do even better, even more genetic. I'm going to like here you go. Oh gosh, yeah, here you go. This one I'm gonna put. Let's see if I can put an arrow here. Okay, that's the normal, and this one here is the weight. I've got to do better than that. We do not know what's the direction of this normal because it changed. Actually, the direction of this normal changed as the motion of the pendulum keep on, as the pendulum keep on moving. Here, this one is the normal. Those are the only two forces that are acting in my physical pendulum, mg. I don't like that. Let's see if I can do better. Yeah, this is a little bit crooked, right? Can I do better on that? I think I can. Yeah, I can do better. Sometimes those things get crooked. There you go. Okay, better. Yeah, better. L, here you go. And then we have the vertical direction. Okay, the vertical direction right in here. Here's the angle theta. And the torque going back, okay, I alpha. Alpha is the angular acceleration. Net torque is torque of the normal, torque of the mg. The torque of the normal is 0 because the point of rotation is exactly where the normal is being applied. The pendulum is moving around this point of rotation. The torque of the weight is mgd sine of theta. You have a negative here because the angle is measured in, because the angle, the unit vector of the angle is in the counterclockwise direction, and the torque is in the clockwise direction. That's why you have the negative. I not with respect to alpha. Okay. And you know, alpha is due to theta dt2. Okay, so here we go. Before the small angles, we can approximate the sine of theta with theta. And that's what we end up getting for the differential equation, right? Why did I put alpha there? Okay, so that whatever goes here inside should be the square root of that, right? Why did I put alpha here? Doesn't make any sense. Huh. Yeah, I put alpha, you know, I shouldn't have put alpha there. So it can mix up with this guy. Yeah, let's do something else. Let's put omega. Yeah, supposed to be omega, 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 omega. Okay. And omega should be the square root of this value right in here. This one should be omega as well, right? Yeah, should be omega as well. Okay, omega. Man, so many alphas there. Let's fix. Oh yeah, here you go. Now we have it. Omega squared is equal to mgd over I naught. Okay. Unit for omega is 1 divided by second. That's now remember, the I naught is the moment of inertia, not with respect to the center of mass. The I naught is the moment of inertia with respect to this point here, with respect to the point of rotation. And we have to get what the I naught is using the parallel axis theorem. Okay? What do we get? We get the I naught is I of the center of mass plus md squared. Parallel axis theorem that we learned in physics 37. The moment of inertia with respect to the center of mass is equal to, for a bar, right? Something like that. Oh. Okay. We can find the period of this pendulum. The period ends up being what you see right in here. Yeah. So for the period, that's what we get for the period. So what we are going to do in this experiment, here you go, let's go to our spreadsheet. Here you go. In this experiment, we are going to do something similar that we did in the previous one. We are going to plot the period of the pendulum. Okay, let's go back to our theory. Here you go. Against, okay, we found that the period is something like that. Okay, that's what we found. So what are we going to do here is the following. Let's see here. Okay, what we're going to do here is the following. We are going to vary this distance, okay? We're going to vary this distance that you see right in here and determine the different periods. It's possible to do that with this bar, okay? In the case of this bar is full of holes. I put just one hole here, but in reality, it has several holes. So you can, let me do a more realistic drawing of this pendulum, you know? A more realistic drawing of this pendulum is something like that, you know? Here you go. Several holes. One, two, three. And because you can hang those pendulums from these holes, on each different hole, you will be able to vary this distance d that you see in there. That the type, but the holes here are small enough so we can neglect their lack of mass, right? That's how the pendulum is, the bar is set up. I'm gonna take this one out. I don't need that, okay? We have even a hole here in the center of mass as well. So by here we have a support. You know, the support is something sticking out, okay, out of our rod. There's a vertical rod, and then there is this horizontal rod that's sticking out. You can place the bar there and put it to oscillate. Then you change, you know, you change which hole you put in there. First you do this hole, then you do another hole, and so on, right? So in the next experiment, you know, the point of rotation becomes this one, this other one here, okay? And now the normal force is going to be this one here, okay? And now the distance is going to be this one. That's how we do the experiment. And we do that for several holes, as you can see. You know, one hole is a distance of 55 centimeters. The other one is a 45 centimeters from the center of mass, okay? And 11, all the way from 11 centimeters to 55 centimeters. And then you get one measurement of 10 oscillations. right? 10, yeah, 10 oscillations, but just like we did for the simple pendulum. But because it's a physical pendulum, the behavior is going to be slightly different. And then what did I do? You know, I calculate this term here, which coincides with what you saw in the, which is this term right in here. Okay, let's go back there. Let's see if that's exactly the same. 1 plus 12 d squared, yeah, 1 plus 12 d squared, divide, yeah, square root of everything. So if this equation is correct, we are supposed to get a straight line. So I'm plotting t in the y-axis and this is square root in the x-axis. Okay, if this equation is correct after performing the experiment, when we plot that, we should have a straight line with this slope. Okay, L remains the same. What doesn't remain the same is D, right? The D is the one that's varied as we perform the experiment. Okay, and that's what you gotta do for today. It's very similar to the other experiment that we did. You plot T and this value here. Okay, let's do that. You already have everything that you need. That should be the theoretical value. The theoretical value square root of what? 2 pi square root L over G, right? Let's see here. Yeah, no, G over L. G over L, square root of G over 12L. No, L over 12G, right? L over 12G, is that right? Yeah, square root of L over 12G, which should be equal, yeah, L over 12G, 2 pi, that's what the square root is supposed to be. That's the theoretical square root. The experimental square root is going to be given by your graph. 12:30 right now. Let me take attendance. Do you know what you have to do? Right? So start with plotting the graphs just like we did before. So here are my notes. We're going to follow almost the same procedure. Yeah, here. Plot the graph, right? Plot the graph to inline mathematical document as an equation. Yeah, display the R square. How to find the statement? Yeah, okay, find the confidence level. Let me see, did I document that before? Must be here. Oh yeah, here you go. Here you go. You're gonna do almost the same thing. There is only one graph for you to plot in this case. In this case, there is only one graph. So here you go. Plot the graph. Okay. T average versus whatever you got there, you know, versus this thing here. Linear fit. In this case, it's going to be a linear fit. There is just one graph. Plot the graph. Let's see, I'm here. Okay, I'll get you. I'll get to you. Hang in there. Let me fix that. Plot the graph. Why is that? Let's see. Plot the graph. Fit the regression. Fit the regression curve. Fit a linear regression curve. Okay, hanging there. Let's see, plot the graph T versus that. the same here. Okay. 2. Fit a linear regression equation to the graph. Okay. Log the slope. Let me see. Log the slope where? In the last table. Log the slope in the last table. Log the slope in the last table. And observe it. Look at the look at the percentage difference. Okay. Work on the units. Work on the significant figures. And finally, determine the CL. Okay. So let me take attendance now. Attendance right in here, P39 lab. Today is the 21st. Okay, Toby, are you there, Toby? Hello, Toby.
Here.
Okay. You download the spreadsheet, Toby?
Yeah, that's what I'm working on right now.
Okay. You're group 1, right? Okay,
Yeah.
yes. Let me put here in the order of groups. Okay, is Brian Spino there? I don't see Brian Spino there. Okay. Next, Pedro Flores. Are you there, Pedro?
Yeah, I'm here.
You downloaded the spreadsheet?
Yeah, I did.
Lawrence? Are you
Yes, I'm
there?
here, Prof.
Okay, good. So don't forget, tomorrow is the exam, right? You gotta be logged into Zoom and Canvas simultaneously. You must
Okay.
have webcam.
Okay.
Kenny?
Okay, so like
Yeah,
last
I'm right here,
semester,
Professor.
for
I
the
got
final?
Wait a minute. Wait a minute. Kenny, are you there?
Yeah, I'm right here.
Okay. Lawrence, did you say something? Did you say anything?
Oh, no, nothing, Prof. Nothing. I got it.
Okay, good. Nolan Williams?
Yeah, I'm here. I got it.
Okay, good.
Professor, you said the test is on Thursday, right?
No, it's gonna be tomorrow, Wednesday.
Okay.
Yeah, the other one is gonna be next week. Yeah.
Okay.
What, Prof? A quick question. Now that I remember, what time is the first exam tomorrow?
12 noon.
12. Okay. So you said you want us to have the Zoom, our webcam on?
Yeah, let me write that down here.
Okay.
You go for the exam tomorrow. You know, one will be on Canvas. Will be on Canvas at 12 noon. 2, you must be logged on Canvas and this Zoom link, okay, simultaneously. Okay. 3, you must have your webcam on all the time. Okay, open notes, open book. However, you cannot have any outside help of anyone. Any outside help from anyone? Anyone? What else? What else? What else? Oh, 2 hours long, right? 2 hours long. If you require more than 2 hours, if you require more than 2 hours, please let me know tomorrow. Please let me know. Please send me a chat message. Send me a chat message. How do you call it? A private site chat message, right? A private chat message, and I will, send your exam. Okay, so
How many questions?
Yeah, it's gonna be around 20, 22. Okay, that's enough for 2 hours. Exam tomorrow, Wednesday. Okay, and don't forget, there will be questions. There will be a few questions. Oh, I'm thinking about 2 questions. There will be a couple. Let's put it. There will be a couple of questions on the lab. Okay, just 2. I'm thinking about 2 questions. 10% of the exam. Make sure that you know what you're doing, right? So let's see. Harun, are you there, Harun? I can't hear you. Okay, Harun, I cannot hear you. I'm gonna put a star here. Musa, are you there?
Yeah, I'm here.
Okay,
Hello?
good. Yeah, okay. Is that Harun or Musa?
Wait, that wasn't me. That was my brother.
Okay, so let's see. Okay, Harun, are you there?
Yeah, I'm here.
Okay, good. Musa, are you there?
Yes.
Okay, good. Daniel Nwagbu,
Yeah, I'm here.
David Nwagbu.
Okay.
Good. Zachary Blue. Okay, good. Zachary is there. Elena.
Here.
I have to the lab notes. Yes, okay, I re-upload the lab notes, yes. Let's see, Luis Crystal. Are you there, Crystal? I see Crystal here in the list, but I need to get some, to hear from you, either to hear from you or type there in the chat box, please. Crystal. Let's go for Dave Myers. Are you there, Dave? I can't hear you. Yeah. Hi, Dave. Okay, I'm gonna put a star here. Can't hear you. And I don't see any message in the chat box either. Robert Faust. Next is Daniel Freire.
Yeah.
Okay, next. Olivia Kruger. Okay, Chuk Lu. Yeah, okay, Amalia Gale.
Here, Professor.
Welcome, Tiffany Wong.
Here.
Okay, next is Anthony Lopez. Next is Safi.
Here.
Thank you, Daniel Yang. Next is Ryan McNeil. Next is Claire Wattinger. Good. George Risk. Are you there, George? I don't see George here in the list. At the very bottom here. Okay, I'm gonna put a star here, George. Jennifer Ramirez. Noah Raymond. Noah. Let's see. Noah, I don't see Noah in the list. Next is Natalie Santiago.
Here.
Okay, Mengshu Zhang. Let's see, Mengshu, I see. Okay, good, thank you. Let's see, Sarina. I can't hear you, Sarina. I don't see any message from you either. Okay, good. Alexis Nigret.
Here.
Next is Darnis Simon. Are you there? Okay, good. Thank you. Olivia Song. Good. Nathan Silva. Good. So let's see how many we have here. Okay, who doesn't have a group? Nathan, right? Nathan doesn't have a group. Okay.
Professor, I'm here.
Yeah, who is that?
Crystal, and he has a kicker.
Okay, Crystal, right? So let me see. Anybody else? Crystal, Dave Dimas, are you there? Dave Dimas, right? Should be the right pronunciation. I don't hear from you, Dave. George Risk, are you there, George? I don't hear from George either. So, do you have a group, Nathan? No. Okay. Do you know anybody here in this class? No. Okay. Okay. So I gotta fit in one of those groups here. I don't want to fit in a group that has 5 students. Okay. You have group number 2. You have group number 3. You have group number 4. You have group number 5. You know, I want to fit you in group number 8 because right now we have, let's see, now we have 4 students. All the 4 are there, right? Group number 7 right now has only 3 today, right? Want to join group number 7? 1, 2, 3, 4. Okay, Jennifer, you can join with Jennifer, Noah, and Natalie plus Mengshu. Okay, so welcome. So group number 7, welcome Nathan, please. And share any information that he needs, like you know, the group folder, right? Group folder link and all that stuff, right? So let me organize that here. Group number, sort. Yeah, group number. Now we have 7. 1, 2, 3, 4, 5. But Noah is not here, right? Yeah, I don't see Noah here. Good. So you know what to do, right? Let me group number 7, right? I'm gonna email. I'm gonna send you through chat the group link, okay? Nathan, don't share this group link with anyone outside your group. Nathan. Here you go. That's for you, direct message. And 12:50. So it's gonna be kind of easier than the other because it's less work, right? Let's see me lab notes. Nathan, I will send you a link to the scored on Canvas. Okay, so let me save that as a PDF file. And I'll post there in the share folder in my Google Drive. Lab notes, this one right in here. Potion, blah, 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 right? So far, we are here. We did the confidence level. Here we go. Wednesday, exam tomorrow. Here we go. Now I will upload it now.
Are we good to go? We don't have any questions.
I didn't hear you. Did you say?
Are we
anything?
good to go? We don't have any questions, Professor.
Wait a minute. Let me finish something here. Then send me
Okay.
a chat message. Send me a chat message, please.
Hello.
Okay, here you go. Lab. I place existing file. Okay. Okay, so it's in there. 1252. Did I upload? Yeah, I upload the notes. You have the notes here. 1138. Good. Are we good to go? If you're already done, okay, you gotta show to me that you have done everything. Okay, I need to know if you plot the graph. I need to know if you work on the significant digits, units, all that stuff. You know, all those tables as well.
Wait, Professor, what are we graphing again?
Is a T average and this big stuff here that you see here.
And what's the regression equation? Like what type of fit is it? Linear, power?
Okay, so here you go.
Linear? Oh, okay, thanks, Professor.
Okay. Here is the relation for T average, right? If you call this guy X, right? You're plotting this versus this. It's supposed to be a linear equation with this slope here. So before you go, if you're going too early, like Daniel wants to go, right? I want to see your spreadsheet there in your group folder. And while you do that, let me go to the restroom. I'll be back. Oh yeah, when is it due? That's a good question. Okay, well reminded. Okay, let's do. Let me give you. Let's see here. Let me take a look at the syllabus. We can give you a better idea. We're doing that right now. We have an exam tomorrow, right? You know, let's do on Thursday, okay? Let's see here. I'm gonna put in the notes. I'll give you 1 day to prepare after the exam. Lab notes. Lab notes. Lab report. June 23rd. Before 12 noon. Okay. 2 hours. Yeah, okay. Yeah, remind me of that tomorrow, okay, Ryan? Yeah. Okay. So George is back. Attendance roster. George. What about Dave? Dave Maes. Dave Maes, are you there, Dave? Let me send him. Hey, Dave, are you there? Now we have how many? 30 here. But you have 33. Why is that? Let's see what's going on here. Noah, are you there, Noah? Nope, Noah isn't there. Okay, that's why. Good, so. So let's see how you are doing. Toby, did you get your graph plotted already? Are you there, Todd? Toby? Okay, Toby is not answering. What about Pedro? Pedro Flores, did you plot? Did you plot your graph, Pedro?
Yeah, me and Nolan are working on the graph right now.
Let's see, Jen. Let's see here. Hang in there. Let me check before you make this modification, okay? The case of Jennifer, right, Jennifer? You can do the following, Jennifer. You can add student 5 here, but don't add a line. I don't want those tables to be moved. It's okay to add, you know, it's okay to put the name of the student here, but do not change the row number of the tables, okay? Is that okay, Jennifer? You understand? It's okay to, you know, put the student 5 here, but don't add a row, nor a column. Okay, I need all those tables in the exact coordinates that they are.
Okay.
Let's see. Who's that? Lawrence? Okay. looks like Lawrence forgot. Good, so let's. Okay, so did you finish the graph, Lawrence? Lawrence?
Yeah, hello, Prof.
Yeah, did you finish the graph?
No, not yet, Prof. Give me a second.
Okay,
Give me a second, Prof.
okay. Kenny?
Can I get back to you when I get it?
Sure, sure.
Yeah, I'm
Just
still
get
working
that
on it,
message.
Professor.
I did not look at it.
Prof?
Let's see, Kenny, did you finish
Yeah,
the
I'm
graph?
still working on it, Professor.
You're working? Okay.
Yeah.
Oh, Professor, this is Toby, and I'm working on it.
Okay. So Nolan,
Yeah, I think I finished it.
the graph?
Yeah.
Okay, did you put the regression equation, R square, all that stuff?
Yeah, I put it in the yeah, I put everything in.
What's the percentage difference you're getting for the slope?
I was getting 18%.
18%. Let me check it. Hang in there. We're group number 1, right? You go. Not this one. Not what I want. Lab 1, lab 2. Whoa, are you getting something like that?
Yeah,
Okay.
it's exactly what I have.
Yeah, I wonder, let's see here. 0.4987, right?
Yeah, that's exactly what I got.
Yeah, let's see. Yeah, it looks like, oh yeah, 18%, just like you said. Well, I suspect that they might have made a mistake here on those 1, 2, 3, 4 data points. That was my suspicion. Let me see here. Let me analyze. Is that the last 4 points? No, it's the first 4 points. Let's see if you get a better. Okay, see, the problem is those 1, 2, 3, 4, 5, 4 points, because I'm getting 0.6669, which is much better. 1, 2, 3, 6, 6, 6, 9, right? Yeah. Now it went down to 8%, right? So if you're in the classroom, I will be asking you. If you're in the lab, in the real lab, I'll be asking you to repeat those 4 measurements here, because those 4 data points are well lined up, right? I would expect a steeper slope. Consequently, my suspicion is that there's something wrong with those 4 points here, those 4 measurements. Okay, but you live this way, don't worry about that. 18% is what you are getting for your data points there. Okay, and start working on the rest, please. All right, once you're done with the plot, linear, okay. Okay, work on the units, sig figs, and CL. Let's go for the next student here in the attendance. Harun. Are you there, Harun?
Yeah, I'm working on it.
Okay, didn't finish, right? Musa,
Still working on it.
you're working, okay. Daniel
Yeah, we are working on it.
and Dave. Okay, good. Who was the student who said he had finished? Okay, let's go there. Zachary. Are you there, Zachary? Yeah, but I put a question mark here. Oh, you're working on it. Okay, let's put that W for working. Next, Elena,
Yes, I'm all done with the graph.
done with the graph. Okay, your group number 3, right? Which percentage difference are you getting for your graph?
I got 13%.
13%, group number 3. Insert. Yeah, see, something happened here. And they have those 2 points too close to each other. Yeah, I do not know what they did here. Now, let's see, 13%, 5323. Yeah, it sounds like 0.5323. Yeah, 13%, just like you said. So, okay, and yeah, there's a problem with this data point and this other data point. I don't understand why it's so close. It shouldn't be close in the horizontal direction. Let me see here. Maybe it's this one 264 and 264. See that? Yeah, there's something wrong about those two. Maybe those 3. Maybe those 3 again. Oh, and those 267 as well. They're close. Oh. Let's see. Yeah, again, if it were in the actual lab, I'll be looking at those points here, and I'll be asking you to repeat those data points. So, okay, so Elena, right? Okay, make sure you do the rest, right? Work on the remaining of the lab. Let's see, Luis Crystal. Did you plot the graph, Luis?
I'm working on it.
Okay, good. Dave, Myers. Dave Myers. Let's see. Yeah, Dave is not answering. Huh? Okay, I won't be able to give credit for Dave if I can't hear from him. If I don't hear from him. Robert, you plot the graph, Robert? Robert Faust. Okay, what percentage difference did you get? .13. Let's see, group number 4. Let's see how it looks like. Group number 4. Insert. Oh man, see that? Oh, that's okay. Add trend line. I suspect that's gonna be on the low side. No, it's gonna be on the high, the high side. 0.7047. 0.7047. We place that here. Uh-oh. Copy. Interesting. Okay. 0.7047. 15%, just like you said. Okay, so move on to the next. Okay. So we can work on this, on the units and the secant digits. Next. Daniel Freire.
I uploaded the Excel sheet as you asked me to, and I did that thing.
You uploaded? Okay. Yeah. That's group number 4, right?
Yes. Did it over?
We get here. Group number 4.
Where's the graph?
Let me see, Daniel Antonio Freire Rosales. Okay.
This is the graph.
Yeah, so I believe someone has a mute here. Okay, so you have, no, not this one. That's lab 1. Right? Yeah, that's lab 1, right? Is that the one you uploaded, Daniel?
No, I uploaded lab 2.
Lab 2. I see here Robert Faust. I don't see.
You have to refresh probably.
It was Robert Faust that uploaded, not you.
No, you
No, there's
probably
another one.
refresh it.
Okay, there's another one here. Daniel Frey. Okay, that's the one. Don't forget, I need only one there. Okay.
No problem.
D4 open.
How
Sorry.
come Excel doesn't copy over the graph correctly?
I didn't understand. What did you say?
Excel doesn't copy over the graph when you upload it from regular Excel to Google Excel.
It doesn't show up right online. Is that what you can see? The graph is here.
You got it, but it doesn't come out nice on Google Excel.
Okay, so yeah, it doesn't come online. You don't see when you're online.
I didn't see it.
See. Okay. Okay. You gotta write down the units here.
Yes, sir.
Check the units before you go. Okay.
Put my name on it.
Yeah. Okay, so let's see. Next should be Olivia, right?
I'm done and I uploaded it.
Uploaded to.
Yeah.
Okay, did you? Olivia. Okay. Download. Okay, Olivia, you gotta work on the secant figures, the units. Okay, I don't see any of that here, right? 15%. Okay. So Daniel, yeah, finish that that was missing, and then you can go finish the second digit, please, Olivia, and then you can go. Okay, here there's second digits here as well. Your work. Okay, let's go to the next student. Finish the graph. Chuck, Lou.
Yeah, I've done the graph.
Okay, and what about the units and the second digits?
I did most of it, but I'm not quite done yet.
Okay.
I had a question though about the confidence level.
Yeah.
Could you like quickly go over how to do that part again? I have forgotten.
Okay, so here you go. You have R is here you go. Here's group 4. Right? You have R square and you have N. Right? You have R square and N. So you go open that table that I provided you all, confidence level table. It's in the shareable folder. N is equal to 8. You gotta look for your R square here. What's the value of your R square? What's the value of your R square?
It's 0.9539.
0.9539. Yeah, that's right. So 0.9539 is between those two values. Okay. So what do you log? You log those two values, 1 minus 10 to minus 4 and 1 minus 10 to minus 5. That's the lower bound, that's the upper bound. So your confidence level lies somewhere between those 2 points, those two values.
All right, thank you.
Okay. And next, attendance right in here. Amalia?
I am currently working on the sig figs.
Okay. So the graph you're done, right? What's the percentage difference you're getting?
The percentage difference. Hold up, let me go back to my. That's
6.09.
right.
It's 6.09.
Yeah,
6.09. You're in the same group? Okay. Okay, good. Okay, so let me know whenever you're done. Okay, Amalia. Tiffany?
I'm done and I uploaded it to the shared folder.
Okay, let me take a look. Okay, group number 6, right?
Professor, could you also check group 2?
5. Group number 5.
Okay, group 5. Okay, let me go through every group first, and then I'll cycle through you. Okay. Group 2. Let's see, Tiffany. This one here, right, Tiffany? Wow, all over the place, right? See those data points here? All over the place, right? Okay, 5, 7. Okay, percentage difference is 6%. Okay. Okay, make sure, don't forget that we are using only 3 decimal places, okay, Tiffany? And
Professor, can you help with one of them, please?
help with what?
With one of those sig figs.
Which group are you?
Same one, group 5.
Group 5. Okay, we are using, here in my course, we are using the resolution of the ruler, of the meter stick. The resolution of the meter stick is 1 millimeter. So you stop at the third, oh, wait a minute. Oh yeah, you gotta be careful here because you put in scientific form. First, put in the regular numeric format, okay? Put in the regular numeric format first. It's not in the regular numeric format. So, and then you refer to the way that I wrote right in here. Here you go. Okay. Third decimal place in meters, but you gotta put in the regular numeric format.
How would I get Excel to do that for me?
Okay, so how do you do that? You wanna know how to do that? So here you go. Highlight the cell, right click the cell, format the cell. Okay. Now you see all the types of format you have, put in the regular number. Okay, put in the regular number and then look what you get. Okay. You use
So we want it in regular number format and not significant figure.
Well, the regular number is have the right number of significant figures, okay?
Oh, I mean not the scientific form.
Yeah, not the scientific format. The scientific format, is a good practice to use this in the scientific format only if the number is less than 0.001, 1000. That's either under this or greater than 1000. Okay, it's anywhere between 1 of 1000 and 1000. You use regular numeric format, unless you have to use scientific format to display the right number of significant figures, right? Sometimes you cannot display the right number of significant figures in this format, and you have to use the scientific format. It's easier to see. Also, it's easier to see the value when you have it in this format. Okay. So let me undo.
Professor, I'm confused on where we enter the information for significant figures. Like we figure out how many significant figures each number has, and then where do you put that information?
Okay, so the number of significant figures depends on the instrument that you use to measure your data. Okay, here you go. We are using a ruler, right? We are using a ruler to measure lengths, right? Ruler and meter stick to measure lengths. So you must, because the ruler and the meter stick has a 1 millimeter resolution, you report up to the 3rd decimal place in meter. Okay? That's how I do here in this lab. Okay, at the beginning, I told you folks that I like to be in the conservative side. Okay, some professors teach differently. Some professors said you can go another decimal place. Okay, but in my courses, I am conservative, so I tell my students to report only up to the resolution of the instrument. In the case of the ruler, is 1 millimeter. The resolution of the ruler is 1 millimeter, which is the 3rd decimal place in meters. In the case of the timer, you know, the timer in your cell phone reports a resolution of 1/100th of a second. Okay, I don't think we are using a scale here in this case, right? Let me see here. Let me see. Yeah, there is no measurement in, oh yeah, there is a measurement in mass here. Okay, yeah, there's a mass measurement. Okay, so in the case of the scale, I you know, because this is a virtual lab, I have to tell you that, okay? I have to tell you that. But if it were a real lab, I wouldn't be telling you that. You would be looking at the instrument and you would be determine what the resolution is. Okay, so that's what you have to know. Make sense? Okay, that's for measurements. That's for measurements.
Okay, thank you.
Digits for measurement. When it comes for a result, here you go. Here's a measurement, here's a measurement, here's a measurement, here's a measurement. The significant figure, oh, here's also a measurement, here's also a measurement. In all those cases, the significant digit is defined, is decided by the resolution of the instrument. In all those cases, because they are all measurements. When you go here for the t-average, in the case of the t-average, it's not a measurement, it's a calculation, right? And the number of significant figures of the t-average is determined by the number of significant figures of your measurements. Usually, you're going to sum those three, determine how many significant figures you have, and then you're going to divide by 3. And also the t-average. Here you go. The t-average is what? The t-average is this value here divided by 10. Okay?
Wait, why did we divide by 3?
Because we made 3 measurements, 3
okay.
measurements. Yeah. We repeat the experiment 3 times, right? And here we divide by 10. Why do we divide by 10 here in this case? Why do we divide by 10 here in this case? Do you remember?
To get the right unit, maybe? I'm not sure.
This is not the right unit. Well, when you did the experiment, you know, you determined the amount of time for 10 oscillations. Okay, that's why 10 oscillations here, 10 oscillations here, and 10 oscillations here. You took the average of 10 oscillations, and if you want to know the average period, then you have to divide this value by 10. That's why we are dividing by 10, because I measured 10 oscillations. The more oscillations I measure, the better result you get. Okay. No need for significant figures here, because it's in red. You do not need significant figures here either. Okay, I should have put in red. Everything else in red, no need for significant figures. Okay.
Okay.
Now wait and attendance. You go, Tiffany. Did I talk to you, Tiffany? I talked to you, right? So you gotta continue. You plot the graph, right? And now you gotta fix the things that I told you. Anthony Lopez. Are you there, Anthony? Oh yeah, I'm done with the graph. Okay, working on sequencing. That's good. Thank you. And Sha,
Yes, Professor.
are you done with the graph?
I'm done with the graph. I got 6.09. And I had a question about the confidence level.
Uh-huh.
So I have a R square value of 0.8779.
Okay.
So that's four. It should be 4 digits, right?
Let me see here. You have 8779. Okay. Okay. And what's the question?
So if it's in 4,
Here you go. Eight data points, right? 8779 lies somewhere around here, right? Between those 2 points, right?
so which one is correct one? Should I get the lower as 1 to the power of -3, 1 minus 10 to the power of -3?
Both. You got the lower one is 1 minus 10 to -3. The
And-
upper one is
Okay.
1 minus 10 to -4.
All right, got
Okay,
it. Thank you.
we have to log both of them. Here you go.
Okay,
1 minus 10 to -3, 1 minus 10 to -4.
perfect. Thank you.
That's the. Any other questions? Let's see, attendance.
One more question, Professor. Sorry, if you could go back to the graph, please, the spreadsheet.
This one here.
Yes. So do we still have to change the value of the red one, its units as well? For the first lab, sorry, I mean for the first lab.
Well, I don't have the first lab here. I have the second lab.
But if it's for the first lab, we have the log and the t average in red. We don't have to change the significant value, right?
No, you chose in red. If you chose in red, there's no need for sequence figures. If that's what you're asking.
Sure, thank you.
Yeah, you chose in red, right?
Thanks.
Let's see attendance. Daniel Liang. Finish everything and have uploaded my work. Okay, group number 6. Group number 6. Okay. This one, Daniel, 121. Okay. Okay, so make sure whenever you have everything ready to go, delete everything else, okay? Please. Let's see here. It's P39, okay, Daniel? And I will correct only one, okay, only one lab. Let's see here. Yeah, you have to have your sequence digits here, Daniel. Daniel? Yeah, Daniel Yang. You don't have the right number of sequence digits here. And okay. What is 9903? 9903. Okay. Okay, so fix that. You don't have the unit here. The unit there. Okay. So let's go for the next one. Ryan. Are you there, Ryan? You're finished? Okay, so let's see here. Did you upload? Yeah, you did, right? No, that's 1. That's not 2. Ryan, that's 2. Okay. Let's download it. Okay. 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 Okay, good. Oh man, look at, is that right? They're all bunching up here. There's something wrong here. Let's see, our group number 6. Let's see here. Yeah, well, yeah. Huh. What a shame. Those guys concentrated all those points. That's not good experimental practice, okay? They concentrated all the points in a single region, and then you have this bunch up of points here. See that? That's not good, the experimental practice. Make sure, Ryan, make sure that you optimize the graph, okay? There is too large of a blank area here in the graph. Okay, yeah, well, there's nothing you can do about that, Claire. Yeah, whoever collect those data points didn't do a good job there. But keep, good. If you want to go, you can go, but don't forget to fix this large blank area here in the graph. Okay, Brian. Attendance. Ryan, finished. Done. Claire, are you done too, Claire? Yeah, Daniel. Let's see, Daniel Liang. Yeah, I believe so. Let me see. Let me take a look. Okay, Daniel, I already saw your graph, right? You can go. I'm gonna put here Dawn here. Let me see, Claire. Did you upload your graph there, Claire? Yeah, you did. Make sure you take out all those spreadsheets, okay? Leave just one when you upload it on Thursday. Yeah. Okay. So here you go. I don't see the equation here, Claire. Yeah, you didn't put. You didn't fill up. Okay, you're not done. So please fill up the. Oh yeah, you should have. All the significant digits here, right? You didn't do the units. Okay, so make sure you finish that before you go, please. All right. Okay, so attendance. So you're done with the graph. What about George? George, are you done with the graph, George? Let me take a look. Did you upload anything there, George? Yeah, I don't see any graphs uploaded by you. I'm going to delete those spreadsheets, okay? Make sure you upload the final one, okay, folks? Group number 6. Make sure you upload so you don't get too much stuff here. Now, George, are you there? Shorten the graph. Okay, how do you shorten the graph? Let me show you. 6. Here you go. Double click in the axis, and then you adjust those numbers, minimum and maximum. Right? Here you go, too. Double click here. Right? Start at 2, ends at 3, maybe. Yeah, there's a problem here because I don't have enough decimal places. Let's see here what's going on. Gonna do it again. Okay, the first thing that we have to do, oh my, 6. The first thing you gotta do in this graph is put more decimal places here so I can see all the numbers, right? That's the first thing. Right click, let's see, already have it here, axis option, tick mark number. Decimal places, we have only 0 decimal places. Let's put 1 decimal place. Yeah, good, we got it. Next, double click again, axis options. So you gotta go 1.5 to 2.5, that's good. So I eliminated some of this space. Now I gotta do that here on the horizontal. Okay, gotta go from 2.5. Axis option, where is that? Okay, 2.5 to 4. Okay, like that. 2.5 to 4, and then you eliminated the empty spaces. Now let's move forward, right? Otherwise, the other students are gonna wait too long. Claire, I talked to Claire, right? Is she working, right? George, what are you doing, George? George, okay, I'm gonna put a question mark here, George. I can't hear you. Here you go, Jennifer. Are you okay, Jennifer? Do you need any help?
We're still working on it, Professor.
Okay. Okay, I'm gonna put that you did the graph, right? And then I'll get back to you. Noah is not there, right?
No, he's not here.
Okay. Next is Natalie.
Yeah,
What are you-
I'm speaking for all group 7. We're still
all group
working on
7.
it.
Okay, you're done with
I
the
got-
graph, but you didn't finish everything. Okay, good. So
We
let's
got
go
the
to,
percent difference.
what do you say?
We got the percent difference if you
Oh,
wanted
yeah.
to.
What's that?
We got 8.27.
8.27. Okay. 8.27. Okay, good. So whenever you get more stuff, let me know, okay?
Mhm.
So group number 8, Sarina. Sarina, are you there, Sarina? Okay, I cannot hear you, Sarina, if you're there. Alexis, are you there? Alexis is coming on board. Are you here? Can you hear me, Alexis?
Sorry, what was that? I lost connection for a bit. I just joined again.
Okay, good. So did you plot your graph, Alexis?
I'm working on it right now. I'm almost done.
The graph, okay. Darnice, right? Are you there? Are you done plotting the graph? I cannot hear you.
Can you hear me now?
Okay, now I can hear you. Okay.
Okay, yeah, I'm just working on my sig figs right now.
Okay, working the same fix, but you plot the graph, right? What's the percentage difference you're getting?
I got 18.67.
18.67, okay. Which is
And we're all
similar.
working together as a group for group 8.
Yeah, okay, good. So what about, thank you, Denise. Olivia, how are you doing there? Working on sig figs. Okay, so you're done with the graph. So, okay, so let's cycle back there to group number 1. Toby.
Yeah, I think we're done and it's uploaded if I'm not mistaken.
Okay, so let me check group 1. Okay, that's the graph. Is that the graph, Toby?
Yeah, that should be it.
Oh yeah, Pedro Flores. Okay.
Yeah, that's it.
Download it. Ryan. Yeah, you can go, Ryan. What time is that? 1:40, almost done, huh? We're almost running out of time here. Let's take a look at your oh. Okay, so let me bear with me. Here you go, must be this one here. Okay, now I should be able to open it. No? Download it. Okay, so here you go. Slope. Okay, those CLs are not correct. Okay, those CLs are not correct. You didn't type the CL in there. You typed the R square. That's a classical mistake that students make. Okay, That's not the right values for the CL. These are the values for the R squared that you put in there. Make sure you fix that, please. You're getting 18%. You have all the units in there. You have all the sequence. Okay, so fix that and then you can go, okay? Group 1. Let's go attendance. Okay, so you have the graphs, right? Graph. Lawrence, do you have the graph too, Lawrence?
Yes, Prof. I'm working with group 1. So
Okay,
yeah.
did you plot the graph?
Yes.
Okay, okay, Kenny?
Yeah, Professor, we're working on the graph.
Okay, make sure you folks get the CL before you go, okay? The correct CL
Okay.
before you go.
All right.
Harun, how are you doing there, Harun? You plot the graph? Harun, hello, hello.
Yes, for group 2.
Yeah.
Yeah.
That's Daniel, right?
Yeah,
Okay, you plot the graph, Daniel?
that is the upload.
Did you finish everything?
Yes, sir.
Let's see, group 2. Harun. Okay, there is, okay, that's one of them. Okay, let's see. 7% difference. R square. Okay, okay, so yeah, if you wanna go, I guess you're in good shape here. You formatted the graph, that's good. You can do better, right? You can cut down to 1.72, cut down to 2.85. You would guess, okay? So if you group, if you wanna go, you can go, unless you have any questions.
Now we're fine, sir.
Okay, good. That's group 2.
Yeah, group 2.
Group 3, Zachary. Are you there, Zachary? I'm fine. Oh, fine tuning. Okay. Do you have any questions so far?
Hey, Prof, quick question.
Yeah, who is that?
Lawrence.
Yeah, what's that?
Prof, so tomorrow you said we're just having lecture but no lab, right? Tomorrow?
Yeah, that's right. The exam is gonna be during the lab.
Oh, okay, for sure. That's all I need to know. Thank you.
Okay, welcome. So Elena, do you have any questions, Elena? Looks like Elena left, right? Okay, Luis Crystal. Okay, oh, you still need to finish sequence figures. Okay, okay, so I'm gonna give you attendance here. Make sure you are there all the time. Okay, that's the first time I hear from you, Dave. Okay, next is still working. Let's put here. Robert Faust, are you done? Group number 4, let's see here. Are you there, Robert Faust? Let's go to the next. Oh, yeah, are you done? Do you need anything else? Okay. Okay. Okay, so if you want to go, let me take a look, a final look here at your graph for the group. Okay, there's a mistake here. If you can figure out the mass, make sure you fix that. Okay, so yeah, that's the only thing I see here. Okay, if you wanna go, you can go. That's group. Let's see here. Faust, right? Amalia, Gail.
Hi, Professor. We're done with our lab. We're working on the hard copy word thing.
Okay, let me take a look here at your lab. Did I see that before?
I believe you.
Not this version, no.
Not this version. Okay. This one here. Okay. Yeah, make sure you fix the y-axis, please. You can put that in numeric format as well. Okay, D. Yeah, you gotta fix the sequence digits here as well. Okay, R square 87. Huh. Okay, so let's see. Yeah, so those are the things I gotta tell you. Okay, let's see. R square. What's the R square here? 8779. Yeah, 8779. Good. So group 5, right? Group 6. Group 6 must be done, right? Daniel Young, Ryan McNeil. Ryan McNeil is done, right? Daniel Young. Yeah, Daniel Young seems to be gone. Claire. Claire is no longer here. George Risk. George is still here. Since you just added Nathan to our group. No, Nathan didn't do lab 1, so don't add him. Okay. Okay, Jennifer. Group 1 has fixed this. Okay, if you want to go, Nolan, you can go. If you're done with the lab. And George, are you there? Yeah, George. I don't hear anything from George. Let's go. Group 7. Jennifer, Noah, Natalie, Mengshu.
Yeah, I think we finished it. We put it in the drive. I'm just wondering where do we want us to put Nathan's name? 'Cause I mean, there's one blank column, so we just added another student there. But do you want to check the document to see if that's okay?
Your group number 6,
Seven.
right?
7.
Let's see here.
It's the one that says completed.
Completed. Okay. Download. Why is not opening? Completed. Here you go. Yeah. Okay. Good. You put his name here. See? You can do even better. Here you go. You didn't change the positions of anything.
Yeah. No, those didn't change.
Okay. Okay. Good. But again, remember to put that in regular font format, in regular numeric format. Okay.
Oh, not scientific?
Not scientific. Yeah. Regular numeric format. Okay. Yeah. Everything here can be in regular numeric format. And this one too can be regular numeric format. Okay, so let me quit this. Next. Group 8. Sarina, are you there, Sarina? Cannot hear, Sarina, cannot hear you. Let's see. Alexis, are you there, Alexis?
Yeah.
Okay, are you
I'm
done?
pretty much done.
You're done? Okay, did you upload your spreadsheets?
Not quite. I'll upload it in a few.
Okay. Make sure you know, make sure you get your final, right? And then you upload it. This one is just a draft, okay? This one that you're uploading now is just a draft. Okay, so it's 1:52 right now. Does anybody needs to, need any clarification of the homework or any help with the homework and the material for tomorrow?
Professor,
Yeah.
quick question. This is Shah. On the online and Google Drive, it doesn't show the chart properly, but if you download it, then you can see it appropriately.
Yeah, I'm aware of that. Yeah.
Thank you.
Okay, so you're done, Shah?
Yes, I'm done completely.
Okay, if you wanna go, you can go. Okay, I'm gonna walk away momentarily from my computer. Okay, if you need help, just call me. Let me take a little break here. I should be logged into this account. Okay, Dave. Okay, my email after class. Okay, so you sent me an email, Dave. Let me see here. Okay. Okay. Yeah, now I remember. Okay, let's talk about that after everybody's gone. Homework number 4, right? Let's talk about that now. Let's see. Chapter 16 is said. Let me see if I can access yours. The date. Okay, here you go, Dave. Okay, Dave. Linear, okay. I'm gonna share the screen with you. Can I share your answer with the class, Dave? Okay, so let's see here. Okay, so he's telling me that this answer is incorrect. Okay, that's what he's telling me. The tension in the string. What is the tension in the string, right? That's what he's asking. Linear density of the string is blah, blah, blah. Transversal is described by the equation. What are the wave speed and the tension in the string? Let me see. Linear density, a transverse wave on the string is described by He didn't say what is assistant use. That's the question that you're asking, right? That's the problem that you're asking, right? Just let's make sure that that's the what it is. Let's see the tension. So what's the equation for the tension? Let's do that together. Here you go. Here you go. Okay, the equation for the velocity, the speed of the wave, right? The speed of the wave is what? V square root. You use this formula. We use this formula is tension divided by mu. Oops. Linear density. Did you use this formula, by the way? Okay, so here you go. Okay, so now let me use the other software that's gonna go quicker. Here you go. V equal to square root tension divided by how do I that? No. Gosh, I forgot. Yeah, this one. Here you go. We want to find out the tension variable. Because we know what mu is because he gave us what mu is. Mu is what? Mu is, okay, 2.5 times 10 to minus 4. 2.5 times 10 to minus 4 kilograms per meter. Kilograms per meter, right? What else do we know? He didn't give us the velocity, right? But he gave us something else. He gave us something else. Okay, so here you go. He gave us the omega. Okay, he gave us the omega, but he didn't give us the velocity. The omega is 38 divided by second. And there is a relationship between omega and velocity. We do know that k times omega is equal to the velocity, right? Is that right? Let me see. K, No, sorry, I made a mistake here. That's not what it is. The proper relation, it's like that. I got the answer. Yeah. Yeah, you got 0.141, right? But you put 1.14 here. You didn't put 0.141. Okay, you put 1.14. That's why you didn't get it right. Okay. Well, this 0.141 is different from 1.14, right? You didn't round it. Prior entries, where is the prior? That's the only one I have here. No, I cannot see the prior entries, but just this one here. Okay. So it's let's see. K times V is omega. Here you go. K times V is omega. Down, and now we can, let's see, K. What's K? K is okay, K is 1.6. Let me finish that here. K is 1.6 divided by meter. Okay, that's what K is. Now we can find out what the velocity is. Let's see. Let me finish the problem. K and omega. I'm getting 23.75 meters per second. And now I can solve for, where's the mu? You go, mu right in here. I'm getting what? Expand. Here you go. Yeah, I'm getting 0.141. Okay. Okay, so you didn't put 1.41, right? You didn't even put 1.4. No, you didn't even put 0.14. Okay, you put 1.14. That's an order of magnitude off. Okay, so that's why you didn't get it. That's why you didn't get this problem, this half part of the problem. I cannot see your prior entries, by the way. Yeah. You go. Yeah, 0.141. That's the right answer. Okay. Is that clear now? You entered the wrong answer there. That's why you didn't get it. Later on, you found out what the right answer, right? Yeah, I cannot see your prior answers now. 1, 2. Let's see. 2, 3, 4. Oh, there are attempt 3. Let's see here. Attempt 3. See that? Attempt history. Let's take a look here. Attempt history. So there is first attempt. You put 10 to the 5th here. That's your first. Oh yeah, I can see. Here you go. Let's see. Second attempt. Yeah, I don't see 0.141 there. Okay. So, okay. In your first attempt, you put 1.41 times 10 to the 5th, right? Times 10 to the 5th. So all of them are incorrect. Okay. Okay, Dave. Good day, Amalia. Thank you for coming. Okay. So, any more questions? Okay, so we have 3 other students there. Jennifer, do you have any questions? Olivia? Let me stop recording.